尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Good morning, participants. Let me make two quick announcements. So, poster presenters, if you want to take your poster back, please come to the poster room with your badge, and the personnel will help you to undo your poster and give it back to you. And please do it before 6 p.m. today. Second announcement is that please don't leave any personal belongings here in a conference room when you leave it. So we will not be able to ship them back after the conference ends. So please make sure that you take all your things with you. Thank you.
Okay, so let's start. Okay, yeah. So let me introduce the first speaker of the day. Is Mauricio Romo from Siemens, and the title of his talk is Quantum Trace Maps and Codimension for Defects. Yeah.
Thank you very much for the introduction. And thank you very much for the opportunity to give a talk in this very important conference. It's a great honor. So let me start with a motivation. So my talk is, I will present some relation between three quantities or three invariants related to hyperbolic tree manifolds, which for all this talk, the manifold is going to be called M, and it's going to be a link complement on S3. So these three invariants are classical topological invariants, such as the hyperbolic volume of M, or for example, geodesic length of loops on M. The other type of invariants is quantum invariants, or maybe more familiar for physicists, objects that you can compute in Chern-Simons theory for different gauge groups, such that the Jones polynomial for gauge group SU2, or maybe Chern-Simons theory for gauge group SL2. And the third is supersymmetric line defects on some particular class of 3D n equal to 2 theories that can be constructed from M5 rings. So the talk is mostly about the relation between 1 and 2. However, I will make some remarks about 3 because it serves as an inspiration and because it's a string theory conference. So this is my outline. I will start talking about the codimension 4 defects and in M theory, and then I will introduce these three objects, SL2, C Chern-Simons theory, the so-called quantum trace map, and the length conjecture, and then I will put all this together to present the main theorem, and if time allows, I will give you a sketch of the proof. Okay. So let's start with codimension 4 defects and the so-called class R theories. So these theories are constructed by putting n and 5 ring together in a space that takes this product form of 2-3 manifolds, where X3, I'm going to take it for this talk to be this squash 3 sphere. And upon performing a partial twist along the M directions, we can compute the expectation value of operators on this M5 ring theory in two equivalent ways. This is, in a nutshell, what is known as the 3D correspondence. One way to compute them, like here, is by using a Chern-Simons theory on M, and the other way is to compute them using some 3D supersymmetric gauge theory that's defined, roughly speaking, by the geometry of M. So the map between which operator you have to insert here and here is the non-trivial part of this 3D dictionary. The operators that we will be concerned in this talk are the ones that you can construct here, this codimension 4 defect, you can construct using M2 or using M5 rings. The only important thing to take into account for this talk is that these operators are going to be line defects in both theories. So you can see here from the diagram how these M2 ring or M5 ring are located. They are line operators in both. And I will focus on this operator, this type of operators. Either if they are M2 or M5, it will be relevant for this talk. So I'm going to describe them first from the Chern-Simons point of view. So from the Chern-Simons point of view, as I said, they are line operators, so they are labeled by, let's say, a loop, for example, inside M, like here, this gamma, and also by a finite rank representation of SLNC. With these two objects, with these two labels, I can construct this trace over R over the holonomy of the SLN connection and compute the expectation value. This should correspond to some supersymmetric line defect on the 3D theory, on the 3D gauge theory. However, I'm not going to talk about this guy. As far as I know, this dictionary is far from being complete. And this talk is about this computation of this expectation. But it's good that you know that behind there is always, you can reproduce all the things I'm going to show by doing a computation on this 3D gauge theory. So in the following, I'm also going to set n to be 2. All right, so let me introduce a little bit about SL2C Chern-Simons theory, which was studied originally largely by Witten. This theory is defined in physics like by this path integral here. More precisely, I should say this is analytically continued SL2C Chern-Simons theory. And is this path integral weighted by the Chern-Simons functional written here. And we have two distinguished coupling constants, one that is reminiscent of the level, this k, that is quantized, and a continuous coupling sigma, which we are going to take it to be real. And when this x3 is a squash-tree sphere, we set them to these values in relation to this b, which is a real parameter. I also am going to define this quantity, h bar, which is 2 pi I b squared, because this quantity is going to appear in many of the expansions I'm going to show later, so it's good to define it. Last but not least, the line operators I'm going to use, I'm going to call them O gamma, where I'm going to set the representation here to be just the fundamental representation of SL2. However, gamma I'm going to allow to also include not just a unique loop like this, but also any quantity of couplings of this loop, okay? So this is I'm going to cover all the operators I'm interested in. So the question is how you can compute the expectation value of such a thing. This is too abstract yet, it's just path integral. So in order to compute any expectation value on this theory, I'm going to use something that was formulated some years ago by several people, between them Dimofte, Hikami, Andersen, and Kashaev, which is called the state integral model. What is a state integral model? Well, it is a quantum mechanical model based on an ideal triangulation of M that I'm going to call like this, delta I. So this is a quantum mechanical model. So abstractly here, I'm not giving you details, but then the partition function, this mysterious path integral, can be computed by has the product of two vectors in an appropriate Hilbert space defined by this triangulation. And therefore, the expectation value of this O gamma boils down to find the appropriate operator in this quantum mechanical theory. Okay, so in order to do that, we need to introduce a few things. Or at least I need to introduce this a little bit about the geometry of ideal triangulation. So I think they appear already in some other talks before, but in order to set notation, an ideal triangulation is composed of a collection of ideal tetrahedron, like this one in this picture. And each tetrahedron shape is determined by these appropriately called shape parameters. These are three complex numbers, Z prime, Z, and Z double prime, which satisfy some relations of this form, two relations. And how these tetrahedron are glued together is characterized by some algebraic equations here that essentially take this form, and they are completely defined by a set of integer or half-integer valued matrices that I call ABCD, and that were highly studied by Walter Neumann and Don Zagier. So the thing to take home from this slide is just that the ideal triangulation is completely determined by these matrices. So given all this data, this state integral model, which as I say is a quantum mechanical model, essentially spit out for you this type of integral. I cannot give you details because of time of how this, what are the quantum mechanics in detail. But at the end, the important thing is that it spit out this integral, which is some Gaussian factor here, which you don't need to learn the details, against some product of quantum dilogarithms, some special functions. The important thing about this integral is that it depends on two parameters. So it depends on h bar, as promised. This is like the coupling constant. And it depends on another complex variable that or variables that I denote x, where x are parameterizing the boundary conditions. In other words, x are parameterizing the holonomy of the connection around some of the boundary, around the boundary torus. So this is something you are free to fix. Maybe if we reach the sketch of the proof, it's going to become more relevant. But by now, just wanted to present like how this partition function will look like if you implement this state integral model. So, okay, so I told you how to compute this partition function, but then the most important question is how you can insert this guy, right? How you can get this, this O hat. How are you going to compute that thing? So how are you going to define this operator? And I will give you first a little bit of a technical definition where this O hat lives, and later on I will try to demystify it a little bit, okay? Because it's a long story. So this O hat operator is actually implemented by injective homomorphism of R modules, where R is this ring, that is called the quantum trace map. So what are these modules? One of them maybe is familiar for some of you, which is this so-called Kaufman bracket Skine module, which is a module whose bases are these symbols labeled by frame links in M. And they satisfy some relations, which are precisely, these are precisely the Skine relations with some parameter Q. The other module here is the so-called quantum gluing module, which is a little bit harder to define, but let's say in a nutshell is a quantization of this space of shape parameters that we had before, this set. So it's a quantization that means you have to put some hats over it, and they are no longer commutative, because everything that has a hat doesn't commute, and you have to put some relations between them. So these relations are rather complicated, but if you are curious, these relations are no other thing but the quantization of these gluing equations here. All right. So these are the two modules. So the punchline is that this O hat that was on the previous formula on the quantum mechanic for a loop gamma is just the image under the quantum trace map of Y gamma. That's the punchline. So now I'm going to try to demystify a little bit this operator or this quantity. So this quantum trace map is not a very mysterious thing. It was around before. It was defined by surfaces by Bonahon and Wong. And more recently, it was actually defined for hyperbolic trimanifolds. And I'm going to cite just two relevant results. One of them is my own work with Agarwal, Gang, and Lee, where we inspired precisely by this codimension 4 defects in the 3D correspondence. We propose a conjecture on what this map should satisfy, which property should satisfy. In particular, some property it has to satisfy is this so-called length conjecture, which I'm going to describe in a few slides. And we managed to prove it, that it satisfied this property for the figure 8 knot. However, our construction in this paper is not very explicit. Like, to be fair, we guess the image of the map for figure 8 knot. However, surprisingly, after a few years, a group of mathematicians defined this quantum trace map in a constructive way. So in a way that you can actually compute its exact image. These mathematicians were Garoufalidis and Yu, and Panichard and Park, which put out papers simultaneously. As a remark, if you find this too abstract and too too mysterious, you can think also of the quantum trace map as a map providing the formation of the classical trace. Namely, if you consider gamma or couplings of gamma and you compute the trace, what you're going to get, if you have an ideal triangulation, is a function, an algebraic function of these shape parameters. So the quantum trace map is just deforming this function by this Q that we defined before, has exponential of h bar. So if you set Q equal 1, this returns to this. So this is a very informal way of thinking of the trace map, but it's useful if you have never seen it before. So before I told you something about the length conjecture, I have to specify some particular infinite class of trimanifolds, which will be complements of twist knots. So twist knots are defined by this diagram here. So there are p twists here on this tangle. And the interesting or the nice property of the twist knots is that its scheme module has already been studied by mathematicians thoroughly. So we know what are the generators of the scheme module, which are precisely elements like this, KVL and KMR. So what is KVL is L couplings of this loop, and KMR is R couplings of this loop, which is the meridian loop. So this objects generate the scheme module. So that means if you want to prove a property of the quantum trace, you prove it for all the elements like this, and you are done. For reasons I'm going to explain later, we'll make there is this remark, which is basically putting powers of Km of the meridian doesn't affect the result too much. It's like rather simple. So the non-trivial part is computation with insertions of this operator, the one that corresponds to L couplings of Kv. All right, so now that said, I have to tell you what is the length conjecture, and with this I can state my theorem. So in order to state the length conjecture, I need to introduce two asymptotic expansions. So one of them is based on the Color-Jones polynomial. So is you take this ratio, the Color-Jones polynomial for Kp for the twist knot, and the Color-Jones polynomial for the twist knot with these couplings of Kv. So in this link, for this link, you color it such that this twist knot has color n, and all the components of the coupling, you color them with the fundamental. After that, you set the formal variable to this root of unity, take n to infinity, and believe me, or it's expected, that you will get a power series in 1 over n, this one. So this is one expansion. So this will be just, this sk are just some numbers. Analogously, or another expansion you can consider is the SL2 Chern-Simons partition functions based on the state integral model that we were discussing. One with the insertions of KVL, which I only sketch for you the idea how you will get it. Again, you set this x to 0, as I mentioned before, these parameters of the boundary related to the boundary condition, and you take the ratio with the insertion of the identity. So this is just a partition function, like that Gaussian integral. Then you take the h bar to 0, and you will get another power series expansion. And this, the only important remark is when you take this series expansion, you have several saddle points to choose on these integrals, and you choose the one that correspond to the complete hyperbolic structure on the twist knot. So the length conjecture can be stated now very simply. It's just the quality of these two expansions term by term. And moreover, the leading term, the S0 or Y0, if you take the exponential, is this function of the complexified geodesic length of the loop, in this case KVL. So it's a cosh of this length. So that's why it has the name of length conjecture, because this is what appears at the leading order. So now the theorem that is not yet out, but that we prove going to be out soon with some punch. We prove that the quality of these two expansions at leading and subleading order, and moreover for all KVL, for all insertions of KVL, and moreover we also prove that if you insert any power of the meridian, this just rescales the numerator by a constant. So it will change the expansion, but in a very simple way. So therefore, it's very easy to implement. The non-trivial part is how to compute these quantities with the insertions of KVL. So that's the theorem. So now in the last, I think I have something like 5 or 6 minutes, well, some quantity, it's okay. I'm going to give you a sketch of the proof, because I think in the sketch of the proof, actually there is some interesting insight. It's not as dry as usual mathematical proof. So let me give you the sketch of the proof. So what I'm going to sketch is essentially how do I get a nice manageable expression for this ratio and for this expansion. Okay, so let me start with some fact. So there is a fact about this twist knot, which is if you take something called the Whitehead link, which is this thing that I took from Wikipedia, and you perform then surgery or then filling along this yellow component with slope minus 1p, what you are going to get as a result is precisely the twist knot complement on S3. So we conjecture, I mean I think we can prove this, but we are not yet there, so I will call it conjecture now. we conjecture that this quantum trace actually commute with to performing the dense surgery. And actually, maybe as a remark, these vertical maps had been studied by mathematicians. So we only have to prove that if you go like this and like this, you get the same. So if we believe that this diagram is commutative, then we can give a very nice expression for this partition function with the KVL insertion, which I'm going to show you in the next slide. So how you do that? Well, you do it in like 2 or 3 steps. First, you start with some ideal triangulation of the Whitehead link, and given that ideal triangulation, which is rather simple because the Whitehead link is not a very complicated knot, you compute use the image of the quantum trace map of loops that actually loops that goes along this yellow, that go like longitudinally, like parallel to this yellow cycle. These are the ones that after you perform the dense surgery are going to become precisely the KVLs. So you compute it in the Whitehead link, and the quantum trace of these loops is actually rather simple. I can even write it here explicitly. Then you compute the state integral model, the partition of this of this Whitehead link with this insertion, so here in blue. So it's like the same thing, same form we had before. I wrote it explicitly just in case you don't believe me, but otherwise the same form, and you insert this blue operator here, which is just this. And now it's just an ordinary integral. And then to implement that surgery, you use a proposal of Bae, Gang, and Lee, which is a proposal from physics, which conjectures that if you take this integral, if you perform this integral against this function, this is equivalent to implement the then filling or then surgery for links or along the appropriate boundary component. In this case, it will be this x1. So once you do that, right, this blue plus this red here will give you the desired state integral for the insertion of KVL on the twist knot. Again, I mean, there are many remarks. Probably Marco in his talk will talk about that, but that all these expressions should be taken as perturbative expression, as defining asymptotic expansion. The non-perturbative expression of this is not clear. So that's why I didn't specify any integration contour on these integrals, because I'm only interested on the asymptotic expansion. So therefore, once you reach this point, you have a general integral form, which the asymptotics are very simple to describe. So this is kind of the most, I think, physically interesting part of the proof. The other part, I'm just going to remark it quickly. Just in order to compute, just to remark that in order to compute this, we had to obtain the exact expression for this color-Jones polynomial of this link with those colors, with those particular colors, and using just some old techniques by Masbaum and Javiro and Le, well, we computed, we couldn't find this expression in the literature. The case L equal to 0 is on the literature, but the case with arbitrary L here is not. However, the expression is rather simple. It's just this is the only non-trivial part when you put L non-zero. So, well, that's a kind of a byproduct of our theorem. So yes, once you have this explicit expression, you can use, as I mentioned, some asymptotics techniques developed by these mathematicians, Chen and Yu, and modify them a little bit to include this insertion. And then you get, again, some integral where you can compute the asymptotics rather straightforwardly, and the theorem becomes just matching the appropriate terms in the expansion. So that's pretty much what I wanted to remark on the sketch of the proof. So thank you very much for your attention.
Thank you for the beautiful talk. Any questions? Yes.
Hi, thanks for the nice talk. So I have a basic question. If I do surgery on my 3-manifold such that it becomes a homology 3-sphere, can you characterize in the field theory language the fundamental group that's left over?
You mean if you start with some cusp 3-manifold, you perform the surgery and you obtain homology 3-sphere?
Yes,
So
and
your
I want to compare this with the regular 3-sphere, so I would want to know what the fundamental group.
You want to know the fundamental group of the homology 3-sphere or of the original one? Or?
Of the homology 3-sphere, so the part that abelianizes to 0 when you...
Very good, okay. So I'm not an expert on that. As I mentioned, for example, the map between scheme modules before and after the surgery, those were developed by Richitsky. I think that may be helpful to your question, but yeah, in our case, we use a very particular dense surgery that we use to obtain the twist knot. So
is there an operator in the 3D n equals 2 theory that is related to these specific moves?
If there is an operator?
Yes, yes. Is there an operator on the supersymmetric theory that captures this?
Good question. Yes, precisely. I said I was not going to talk about that. Yes, but because I think in the supersymmetric theory, I mean, the operator it should be whatever this the one that implemented the surgery. It should be something like this, right? Whatever this thing is, interpret in the supersymmetric side. But the main problem here is that for as far as I understand, because I haven't looked at this 3D correspondence in several years, but for several 3-manifolds, it's very hard to determine, for example, the exact gauge group of the corresponding supersymmetric gauge theory. So it's, for example, already determining what is the image there, the 3D dictionary for these operators, these line operators, is already hard. You can do it for simple 3-manifolds, such as figure-8 knot, for example. Then you can, but otherwise the map is too incomplete.
Okay, thank you.
Yes.
Thanks, Mauricio, for the nice talk. So could you comment on the relation to the original volume conjecture? Because it looks like the first quantity you have is more related to the original volume conjecture by Kashaev, and the second quantity you have is related to the Andersen-Kashaev volume conjecture for the state integral.
You mean comment about these things, no?
Yes, how your result generalizes standard volume conjectures.
Yeah, so the case of, this is like a variation of the standard volume conjecture. So for the standard volume conjecture, you don't have you don't have this numerator. You just have like the denominator if you want. And here is the same thing. You just have the denominator. So here, because you put the ratio kind of to cancel the volume part. And what is the subleading is something that depends on the length of this loop measured with the complete hyperbolic metric. So that's the relation, yeah.
Well, let's thanks the speaker again. And without further delay, let's start the next talk. All right, so the next speaker, Victor Rodish from UC Santa Barbara, and the title of his talk is C equal to 1 string as a matrix integral.
Okay, so thanks to the organizers for putting together this wonderful conference and for the opportunity to speak. So today I'll tell you about a topic that is a little bit old, but we'll connect it to newer stuff. So this is based on a paper that appeared a couple of months ago with this awesome collaborators listed here, or pictured here, Scott Collier and Lawrence Eberhard. And it also builds on earlier work with another awesome collaborator, Beatrix Mollman. And Well, as I said, C=1 is a vast subject. So in some sense, it also builds on the work of many people, many of which are here in the audience. And here are some reviews if you like to learn more about this subject. OK, so even before we begin, let me just give you the punchline. The punchline is that C=1 string theory is dual to a 0 + 0 dimensional matrix integral. So together with an older duality, with a matrix quantum mechanics, this constitutes a triality. So the new place will be here on the right. OK, here's a brief outline. I'll begin by trying to make a distinction between minimal string theory and 2D strings. Of course, the upshot will be that they're actually not different, but I'll begin like that. And then I'll tell you how we obtained this, this matrix integral duality from a newer, more recent string theory, the complex Lewis string, which is a minimal string. Lastly, I'll tell you that we don't exactly land on the S matrix, but something slightly bigger, which we might call discretized amplitudes. Then I'll present briefly the spectral curve and its associated topological recursion. OK, but before we get there, so why do we study low-dimensional string theory? Well, the reason is that it's a controlled laboratory for quantum gravity and holography, where exact tools are available, like CFT, matrix models, analytic bootstrap. So we can test the big ideas of duality, emergence, wormholes, and whatnot, where calculations are feasible. And I like to emphasize that these are not just toy examples. They are UV-complete string theories. So in this sense, we can hope that some of the lessons that we learned in these models generalize to higher dimensions. And a nice example of that I like to keep in mind is the story of the instantons. Last but not least, there's been many recent applications from these toy models, ranging from 2D quantum gravity, non-perturbative effects, to low-dimensional holography in 2 and 3D, sometimes including de Sitter, as well as revealing some nice corners of the landscape, which I'll come back to in a second. OK, so let me begin trying to make this distinction we might call minimal strings and 2D strings. So let me begin by saying what is the thing that is common. So all these models have the same ingredient, which is Liouville CFT, and together with the BC ghost. So they only differ by the junk that you complete it with to form a critical string. Now, a difference, perhaps a philosophical difference, is how we think about them. So let me remind you that in string theory, we usually have the worldsheet CFT, but what we actually care about is how this worldsheet is embedded in space-time. But in minimal strings, we typically think about them as just models for quantum gravity on the worldsheet. And on the other hand, C=1 string, we usually think about it more standardly as strings in a target spacetime, which is also two-dimensional. A slightly more concrete difference is their holographic paradigm. On the one hand, minimal strings are dual to matrix integrals, 0 + 0 dimensional. And on the other, 2D strings are dual to matrix quantum mechanics, 0 + 1 dimensional. OK, so now let me tell you a little bit more about minimal strings. So first, let me tell you about the older models. The first example is where you couple Liouville CFT, the common ingredient, to a 2, p minimal model. So this is a discrete family that, if I plot it in the central charge space of the junk CFT, it forms this discrete family. OK? And these turn out to be dual to a single matrix integral. The next older example is the slightly more general version with a p, prime minimal model. These are still discrete, but they form a dense set in yellow. So these are dual to 2 matrix integrals. The slightly newer ones, one first example is the so-called Virasoro minimal string, in which you couple Liouville CFT to something called time-like Liouville CFT. This forms a continuum family, which, in particular, in the large central charge limit, reduces to the JT gravity matrix integral duality of Sawchenko and Stanford as a theory of quantum gravity on the worldsheet. Lastly, another new model is the complex Liouville string, in which you couple two complex conjugate copies of Liouville CFT with central charge 13 plus and minus I lambda, so you can think about it going along this direction. And distance has to be dual to a two-matrix integral. And this is the one that will play a role today. Now, the defining locus of this last one in blue is this vertical line, but when the dust settles, it has very nice analytic properties. So starting from this, you can go beyond this and cover more of this complex plane in central charge. This is a slight exaggeration because we still don't know exactly how to recover all the other ones from this blue one, but that's the expectation. And in fact, today we'll see an example of that. So today we'll focus on one particular point of this landscape where the central charge is equal to 1, in which seemingly things are dual to matrix quantum mechanics. And a summary of this talk would be that we'll obtain this new duality starting from this complex Liouville string and its duality with a two-matrix integral down to the c equal to 1 string in this landscape. Okay, now let me spend a little bit of time telling you how we think about a 2D strings. So this particular point. Okay, so here's the worldsheet again. Time-like-free boson, which we interpret as time, and the Liouville CFT, whose field phi we interpret as space. Here's the action for Liouville. Now, recall that what controls the string coupling is whatever multiplies the Ricci scalar in string theory. So the string coupling behaves like this. So what we learned is that the string coupling depends on where you are in space-time, in space in particular. So when phi is large and negative, you have weak string coupling. And when phi is large and positive, you have exponentially large string coupling. But then there's the purpose of this last term of the Liouville action, the so-called Liouville wall, that shields this potentially uncontrolled region of very strong coupling. And the observables are nothing but scattering amplitudes of closed strings that come in from the asymptotic region, come here with string coupling is non-zero, interact with each other, bounce off the wall, and go back to the asymptotic region. So this is, I'll denote the S matrix by capital S, or S hat. S hat will just mean that I'll strip off the energy conserving delta function. And these are computed as usual as correlation function in the worldsheet CFT integrated with the relevant moduli space of the string diagram. The first example pictured here, the 2 to 1 scattering amplitude, turns out to be fairly trivial, so it's just 1. But let me give you a couple of slightly less trivial examples, just so that you see how this look. So for example, the 3 to 1 or the 2 to 2 scattering amplitude take this form, simple polynomials, and for example, this 2 to 2 amplitude has this interesting non-analyticity with the max function, or the 1 to 1 reflection amplitude of one loop from this diagram. Now, these look deceptively simple, so at least let me try to convince you that these are very non-trivial. So let me show you what would entail to compute this amplitude, this last one. So here's a slightly ugly formula. This is a particular conformal block decomposition of the Liouville correlator through higher genus conformal blocks, integrated with the moduli space. So this is a little bit of a nasty computation, but it has been done. And the claim is that when you do this, you recover this simple function, the simple polynomial. Okay. I won't have time to discuss this, but of course this, from the matrix side of the duality, this can also be computed through the matrix quantum mechanics, and in particular was completely solved by Moore, Plesser, and Rangulam in 1993. Okay, but at this point you might wonder, so the DOCC formula was discovered a few years after the matrix quantum mechanics was solved. So you might wonder, what did people do, even just to check this duality, before knowing what Liouville CFT was? Okay, the answer is resonance. The answer is they evaluated these amplitudes for very special kinematics, for very special points, in which the sum of the energies saturates something called the background charge. And in that particular situation, the special points, the Liouville correlation function reduces to a free linear dilaton correlation function. Since it's free, then you can perform the calculation, and you can check these formulas in special cases. So that's what people did, as explained by De Francesco and Kutsov. Okay, so now let me tell you the route that we took to arrive to this duality, and this was from starting from the complex Liouville string. So here's the Wool sheet again of the complex Liouville string, this slightly newer model, which is 2 complex conjugated Liouville CFT with central charges 13 plus and minus I lambda, so that the sum together with the goats is the total central charge is 0 and is a critical string. The observables in this case are, again, the amplitudes, integrated correlation functions of the ingredient CFTs, integrated over the moduli space of the string Wool sheet diagram. Okay? So these are complicated functions. These are no longer polynomials as in the previous examples, but suffice it to say that these, at least in low genus, can be explicitly bootstrapped. Okay, and this was done. And at least now we know explicit expressions for these amplitudes, say, for example, through topological recursion. So I'll show you a formula in a second. Okay, so this is the main slide. So how do we go from the complex Liouville string to the C=1 string? So the stuff on the right is the same stuff, just Liouville CFT. So the basic operation we want to do is go from one copy of Liouville CFT to the free boson. So what do? So in fact, So in fact, the answer was already given earlier in this talk. So if you were paying attention, you already know the answer. So I'll give you a couple of seconds to see if you can figure it out silently on your seat. Okay, so the answer is, again, the special kinematics, this resonance computation. So what you need to do is to saturate the background charge such that the Liouville correlation function reduces to a free correlation function. More precisely, the statement is that along special kinematics, where the sum of the momentum saturates the background charge, in this case equal to 0, relevant for C=1 strings, there's a pole in the correlation function of Liouville CFT, and its residue is the free boson correlator. So that's the thing you need to do, extract this pole. Okay, so that's the main upshot. And let me just a word of warning. In principle, this is at the level of the integrand, so we can trust this when the amplitude of the complex Liouville string is convergent. But away from that is not necessarily clear. And this is related to the fact that we'll come back shortly that we'll obtain actually something slightly bigger than just the S matrix. We'll get something that we'll call discretized amplitudes. Okay, you can ask me more about this later. Okay, so now we know what to do. So now let's do the computation. The most direct way to do this is through this intersection number expression for the amplitudes of the complex Liouville string. So this is a slightly complicated formula, but at least let me unpack the conceptual points of this formula. So it's a sum over stable graphs. So a stable graph means all possible degenerations of a Riemann surface. So for example, here's the 4-point amplitude. There's 2 contributions, one from a content interaction and one from a degenerate one. You can think about it as an exchange diagram, where the Riemann surface has degenerated in the middle here. They're colored, meaning that there's an integer associated with each vertex that you're instructed to sum over. And just like in Feynman rules, this expression on top tells you what are the actual factors associated with the vertices, with the propagator here, and with the external legs. So this is what the formula means. Okay? And you can think about it, if you're familiar with topological recursion, as specifying the same data as topological recursion. The actual numbers are written in terms of this homology classes, but it will not be too important for today's talk. Okay, but at least we know what to do. So you take this formula and we extract the resonance residue at the special kinematics. And then we'll take the limit of the central charge going to 1, because that's the relevant case here. And I'll do one more thing of going from position space to momentum space in the result that I'll show you in the next slide. Meaning that we'll trade these colors for an actual momentum. Okay? So let me show you what you get. But before that, let me tell you the main feature that arises after doing this calculation. The main feature is that we don't exactly land on the S matrix. We land on something that looks more like a discretized amplitude. So instead of having energy conservation, momentum conservation, we have momentum conservation up to an integer. So we get a Dirac comb. Okay, the picture to have in mind is that you have the Euclidean time, but it's discretized. So the analogy here is like atoms in a crystal lattice, and we're studying phonon scattering amplitudes. Okay, so that's a picture. Now let me show you the result for this hatted lowercase s. So after you do that calculation, you end up with this particular presentation of the amplitude. Again, it's written in terms of a sum over Feynman diagrams. Here's an example of one such diagram. And let me unpack the ingredients before giving an example. So the first ingredient here is that the vertices are given by somewhat surprisingly, the amplitude of a different string theory. In this case, the Virasoro minimal string. A bit surprising that some other string theory appears as a building block of this one. Okay, but these are known and are, in a concrete sense, these are deformations of Mirzakhani's Weil-Petersen volumes. So these are also polynomials in the momentum. The second ingredient is the propagator factor, so PE being the momentum of the edge here, the propagator. But, as we were discussing before, shifted by an integer that we sum over. Lastly, as in any Feynman diagram, if there's loops in the Feynman diagram, then you're supposed to integrate over the loop momentum. Except that in this case, the loop momentum is only integrated over a finite interval. So that's the formula. Let me show you an example. And in a second, I'll show you how to go from this discretized amplitude to the actual Lorentzian S matrix. But first, an example. As I told you, the 4-point amplitude has two contributions, one from the Conrad interaction and one from an exchange interaction. The formula that I gave you before instructs us to, for every vertex, plug in a factor of the Virasoro minimal string amplitude, like this, which are known functions, then a propagator for this case, and then summing over all possible integer shifts. Okay, so plugging in the known functions and performing the sum, you obtain a formula like this, some polynomial, but importantly, periodic Bernoulli polynomial here, whose argument is the fractional part of the exchange momentum here. So this curly brackets means fractional part of. Okay, here's the answer again. Now let me try to explain how you go from this formula to the Lorentzian S matrix. So we'll do that in 2 steps. The first step is what we might call restricting to the first Brillouin zone, meaning that we'll restrict the momentum and all possible exchange momentum to be small enough so that it doesn't really see the periodic nature of the spacetime. In this case, less than 1. In such a situation, we can simplify the Bernoulli polynomial down to absolute values. So in this case, I wrote it as a square root. So that's the first step, just restrict to the first Brillouin zone, which we might think in this cartoon as just focusing on momenta small enough that you only see this part. The second step is to Wick rotate to Lorentzian signatures. Okay, so we rotate the Euclidean momentum to Lorentzian energies. To do this, you have to keep track of to choose a consistent branch choice here. And with the choice that we made, positive energies correspond to in states, and negative energies correspond to out states. Okay, so you plug that in into the Euclidean formula, Wick rotate, and you obtain this formula in blue. Finally, the Lorentzian S matrix element. Okay, so this is the answer. And of course, you can choose particular kinematics. For example, the 3-to-1 process or the 2-to-2 process, and you recover the formulas that I showed you earlier before. And of course, they agree with the matrix quantum mechanics. Okay. Of course, you can try to do more complicated examples with the same Feynman rules that I showed you. If you think about this, it's kind of horrible to try to do directly, but with these Feynman rules, you can readily do so. Okay. Now let me briefly present the matrix integral side of the story, rather briefly. And here, I'll phrase it in the language of topological recursion. Okay, so in a sentence, topological recursion is a recursive reconstruction of all the observables, perturbative observables of your theory that obey the loop equations of a matrix integral. Hence the relation with the matrix integral. So that's at least in a sentence. But for now, it suffices to say that it's at least a machine that takes as input a complex curve parameterized by x and z and y. And what it outputs is all the string amplitudes recursively to all genus. Okay? This is due to Einar and collaborators. Okay, so this is the result for the associated spectral curve. It's a simple function. It's a cosine and a sine, where z is a complex parameter. Let me say 2 comments. The first is that, well, it satisfies the simple equation of a circle, or more precisely, a complex sphere. And for those who are familiar with the matrix quantum mechanics, if you squint at it, it definitely looks like the equation for the Fermi surface. And in fact, following this type of reasoning was already, this spectral curve was written down by Alexandrov many years ago already. And from a slightly different perspective, it was also studied by Dashkov and Vafa, who interestingly also pointed out the discretized nature of the spacetime, at least for the compactified C equal to 1. Well, okay, so here we obtained it directly from the will sheet and then explained how to recover the physical S matrix. Okay, and just a comment for the experts, it's important that, that this spectral curve is infinitely sheeted sphere and infinitely many branch points, which is relevant for the topological recursion. So here's my attempt to make a drawing of this complex curve. Okay, and slightly more explicitly, topological recursion takes the following form directly for the S matrix elements. It's explicitly written here in gray. The precise form is not super important. Perhaps it's easier to remember the structure. Is the different topologically distinct ways of building a high Riemann surface by gluing in a pair of pans. So this constitutes a version of Mirzakhani's recursion for Weil-Petersen volumes, but here for the discretized amplitudes, which now have a notion of in and out momentum. Okay, but just let me note that this is a recursion for the discretized amplitudes, not the S matrix directly, because some of the terms here involve processes that don't exactly conserve momentum, but only to mod an integer. So we don't have a recursion for the Lorentzian S matrix, but only from this discretized ones. But we can recover the Lorentzian one, as I described earlier. In my last minute, let me end here with a lesson that I think is kind of nice. So at least there's 4 different approaches to 2D quantum gravity, at least. One of them is matrix integrals that arises by thinking about discretizing 2D spacetime. The second one, topological gravity, which has more of a cohomological nature, intersection theory in moduli space. A third one is the gravitational path integral. And of course, the fourth one is string theory, which is a larger framework which nicely incorporates some of the previous ones. So I think one lesson from this is that the first 2 are not just capable of computing quantum gravity-ish observables like intersection numbers, volumes, partition functions, but also something that, like, as particle physicists like to think about, the S matrix of particles. So I think that's kind of nice. So with that thought, let me pause here for questions. Thanks.
Well, thank you, Victor, for the beautiful talk. Any questions? Yeah.
Could you view this amplitude with, your theory with the discretized momenta, or momentum conservation up to an integer as a result of condensing a closed string tachyon or turning on the closed string tachyon? It would be a periodic field in the Euclidean time direction.
Yeah, that's an interesting thought, meaning that the tachyon obtains a periodic profile in spacetime. That's an interesting thought. I haven't thought about it that way. Thanks.
Other questions? Yes, Rob, comment?
Thanks for a nice talk. So you mentioned our work with digraph. In that context, we were talking about C equals to 1 at the self-dual radius, which is equivalent to Gaussian matrix model, and n-fold covers of it, which are basically, you can unwrap the circle. So we got the answer for n times self-dual radius, and you can take n to infinity to get the full real line. Can you get, from your Liouville perspective, arbitrary radii as matrix integrals also, or only these integer copies?
Oh, you mean coming back to the compactified
coming back for arbitrary radius in the Euclidean language, for if you come back for arbitrary radius.
Yeah, that's a great question. The answer is that we haven't tried. And one thing that we in particular would like, if we try to go that route, is trying to, something that would be interesting is trying to also capture, through this topological recursion, winding modes, which I particularly don't know how that sort of would unfold, but that's an interesting question, and we haven't done it.
Any further questions? At the very end, yeah.
Yeah, thanks for the nice presentation. I was wondering, this kind of C charge, right? What kind of interpretation is that? Is the charge of the amplitude or the charge of the strings? And here.
Ah, okay, thanks. Yes?
So this C equal to 1 is the charge of the string, and what is the physical interpretation? And would you expect this triality be found also in C equal to higher value?
Okay, so let me try to unpack the question. The physical interpretation is what I said, that it's some sort of, in target space, at least the discretized amplitudes are in Euclidean signature, and it has this discretized nature, kind of like a crystal lattice. And then I showed that for the first Boolean zone, you can rotate to Lorentzian signature, and it's a more or less standard flat space, two-dimensional space-time. Now, your second question was, can we find other trialities for other models, like the first ones that I showed? And I think that's an interesting question, and I would hope that the answer is yes. And so just to phrase it a bit provocatively, I think something that could be kind of fun is to, for instance, maybe find a matrix quantum mechanics dual to JT gravity, maybe. That might be wishful hope, wishful thinking, but it's a possibility. So thanks for the question.
Okay, thank you.
Yes, over there. Yeah.
Victor, I have two questions. First one is a bit technical. So you mentioned instantons in the beginning. Do you see how this triality, this perspective from the matrix integral help you to understand non-perturbable effects in the quantum mechanics?
Non-perturbative effects in sequence one string have been more or less understood. Well, they have been understood on these two sides. And you say, well, how do they arise here, right? Just in general, in matrix integrals, they also have been understood, non-perturbative effects. Except C equals to 1 is kind of like a degenerate case. Instanton are associated with, I forgot the word, with self-intersection points of the complex curve. But as you can see in this case, like the curve intersects itself on a continuum of points. So it's a little bit degenerate. So it has been studied, for example, in a paper by Alexander Mahajan and Sen, that they needed to deform the theory a little bit with a sine-Liouville deformation to separate the instantons into single points. So it can be done, but it's just slightly degenerate in this case.
I see. So the problem is with the integral, multi-line integral for the instantons. Is that the subtlety?
Sorry, can you repeat?
Oh, I can ask that afterwards. Maybe I can ask the philosophical question. So here it seems that from the triality, there's some notion of emergent time.
Right. Oh, yes.
How do you make of that? Like, what is the general conceptual mechanism that's behind this emergence?
I should say that that's still something that to be studied in more detail. There's the one connection that goes back even to earlier papers by Gross and Klebanov and friends, that the idea is that you consider a matrix whose potential is kind of like a chain, and you take a particular continuum limit of it. And that would bring you from the matrix integral of the chain of matrices to the quantum mechanics. But I should say that To my knowledge, this hasn't been studied super carefully, but I think it's a nice thing to think about.
All right, so maybe let's have a break and come back at 11 o'clock. Yeah, thank you.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Well, welcome back. Our next speaker is Marcos Marino from University of Geneva, and the title of his talk is an overview of resurgence. Let's welcome.
Okay, can you hear me? Yes. Well, first of all, let me thank the organizers for the opportunity to give a review talk in this string conference. It's really a great honor. So I'm going to give an overview of resurgence, and let me start by trying to learn how to use this. Okay. So resurgence is motivated by two questions. The first question is, what is the behavior of perturbative series in quantum theories, and what kind of information is encoded in that behavior? And the second question is, can we use perturbation theory, or perhaps an upgraded version of perturbation theory, to calculate exact non-perturbative answers in quantum theories? So historically, these questions arise very naturally after the success of perturbation theory in quantum field theory. And already in 1952, Dyson addressed the first question in the case of QED, and he famously argued that the perturbative series in QED must have a zero radius of convergence. Now, these questions were explored even more intensively in the 1970s and the early 1980s, and a first success of the theory of resurgence in that period was in the context of quantum mechanics. It was the upgrading of the WKB expansion to an exact method, which is now called the exact WKB method. And in the same period, in the early 70s, 80s, an original mathematical framework for resurgence was developed by the French mathematician Jean Écal. So after this first period of developments in resurgence, the ideas of techniques of resurgence have been applied in many different contexts and many different guises. And I think the main reason I'm giving an overview talk here is that more recently, these ideas and techniques have been used in a more systematic way in what I would call the stringy ecosystem. So they have been applied to theories and models which are part of or close to string theory, like matrix models, Chern-Simons theory, topological strings, and so on. And another reason for the resurgence of interest in resurgence is the availability of computer-generated long perturbative series in which we know many, many terms, which are always the kind of best starting point for a resurgent analysis. So in this talk, I will present a partial overview of the subject due to time limitations, and I will also try to focus on topics which have not been addressed in previous string conferences. Okay. So let me start with a crash course on resurgence. What I'm going to do now is to give you some mathematical tools which are precise enough to address the kind of questions that I was asking before. Okay, so let's start with the first question. What is the behavior of perturbative series in quantum theories? Now, the first thing to note is that typical perturbative series in quantum theories are factorially divergent. Their coefficients grow like n factorial, and this is why they have a zero radius of convergence, as Dyson argued. But we'd like to do a little bit better. We'd like to have a quantitative understanding of this factorial behavior. And one way to do this, and it's relatively easy to see mathematically, is to address a different problem, which is to understand the singularities of the Borel transform of the perturbative series. So this looks a little bit scary. Let me give you some details on how this goes. So let's suppose that you start with a formal perturbative series in which Z plays the role of the coupling constant and AN grow factorially. So the Borel transform is another series in the variable zeta in which you take the coefficients of the original series, AN, and you divide them by n factorial. When you do this, you calc the factorial behavior, and you get a series which is actually convergent at the origin. So let me give you a very simple example. Suppose that you have the simplest possible factorial series in which the coefficients are just n factorial. Now, the Borel transform is going to be given by 1 over 1 minus zeta, and you see that there is a singularity at zeta equal to 1. And this simple pole reflects the factorial behavior of the original series. So the message here is that factorial growth is going to be translated into singularities of the Borel transform. And a very important aspect of resurgence is when you expand this Borel transform around a given singularity, you will generically get new formal power series. And this is one of the most important aspects of the story. So let me give you a simple example. Let's suppose that you have a logarithmic singularity in the Borel transform, which is a situation which happens very often in quantum field theory and string theory. So if you expand the Borel transform around a singularity at zeta equal to zeta omega in what is called the Borel plane, and you express this in terms of the local coordinate psi, you will find a logarithmic term, and multiplying this logarithmic term, you will find an analytic function at psi equals 0, and depending on the normalization of this series, you will get an overall constant S omega, which is called the Stokes constant. So the main point here is that the local analysis of the Borel transform as singularity gives you two pieces of information. One is the Stokes constant, which gives you the overall strength of the singularity if you want. And then you will get a power series that I will obtain by taking this analytic series at the origin and multiplying all the coefficients by n factorial. So the series that I will attach to this singularity will be also factorially divergent. And we will understand in a moment why I do this operation of multiplying the coefficients by n factorial. But that's the main, important message here. Given a singularity, you can extract information from it. This information is encoded in these two pieces, Stokes constants and informal power series. And now you can go through all the possible singularities of the Borel transform, and you will collect all this information in a collection of power series and Stokes constants, and this is called the resurgent structure of the original perturbative series. And this is a mathematically precise and useful way to encode the factorial behavior of the original series in this information set. And it's actually going to be very useful because, as we will see in a moment, this power series will tell us about sectors of the theory which go beyond the perturbative sector. Okay, so this is the first step addressing the behavior of perturbative series, and this is the mathematically correct way of doing it through this resurgent structure. But remember that there was a second thing that we wanted to do. We wanted to obtain exact results. If you want to obtain an exact result, you have to have a function. You have to, in a sense, get functions of the coupling out of the perturbative series. And the way to do this in resurgence is by doing what is called a Borel resummation. Now, a Borel resummation of a formal series phi z, that what we had before, is simply the Laplace transform of the Borel transform. And this is simply because the Laplace transform is the inverse, the formal inverse of the Borel transform. So when you do a Laplace transform of a Borel transform, you reconstruct, in a sense, the original object. But we have to be very careful here, because remember that I told you that this Borel transform has singularities. So you might have singularities when you do this Laplace transform, and you have to avoid them. And the way to avoid them is to deform the Laplace integration contour into different ways. You can deform it above the singularities or below the singularities. And the objects you obtain in this way are called lateral Borel resummations. When they are well-defined, they are functions of the coupling, and they have the property that when z, the coupling constant, is small, you recover asymptotically the original perturbative series. So lateral Borel resummations are machines that transform a factorial divergent series into actual functions of the coupling and give you the possibility of obtaining exact results. Now, one very important thing is that these lateral resummations are going to be different precisely when there are singularities along the integration contour, and the difference between them is called a Stokes discontinuity. And this is the resurgent version of the famous Stokes phenomenon on classical asymptotics. And another important aspect of Stokes discontinuity is that they encode information along the singularities along the ray, and they give you exactly the same kind of information that we were finding before. For example, you take log singularities again, it's very easy to calculate the difference between these two lateral resummations, essentially by using residue theorems and complex analysis, and you will find that the difference involves, again, the Stokes constants associated to the singularities. Then you will have an exponentially small term involving the location of the singularity, and then you will have this series phi omega after lateral resummation, and this is the reason why we were using this series phi omega, because it's the one that appears naturally in Stokes discontinuities. Now, perhaps the most important aspect of Stokes discontinuities is that they suggest you something very important. They suggest you that the natural building block of the theory is not the formal perturbative series that you started with. The natural building block of the theory is obtained by adding to the perturbative series exponentially small corrections in the coupling constant. And the object that you obtain in this way is perhaps the central object of resurgence, and it's called a transseries. Okay. So a transseries is simply your original formal perturbative series plus a series of exponentially small corrections multiplying also factorial divergent series. And in order to specify a transseries, you have to tell me what are the coefficients here, and these coefficients are transseries parameters. Of course, the main candidates to play this role here of corrections for perturbative series are the series that were obtained by Stokes discontinuities. But in principle, you can add a more general set of corrections. Now, the way we will construct functions in resurgence is by using lateral Borel resummations of full transseries. So in previous to all the developments in resurgence, people were doing Borel resummations of just the perturbative series, and the key idea here is that if you want to reconstruct exact results, you really have to consider full transseries, And the lateral Borel resumations of full trans-series is called sometimes a Borel-Ekal resumation. Now, a very important point here is that due to Stokes discontinuities, these trans-series parameters are only well defined up to jumps by the Stokes constants. And this is a very important fact of resurgence, is that the strength of a non-perturbative effect is not intrinsically defined. It depends on how you decided to resum the perturbative sector. You can resum it with one lateral resumation or with another, and this will change the value, the strength of the non-perturbative effect. So the strength of non-perturbative effects is not uniquely determined, and this will play a role in some physical examples that I will show you in a moment. Okay, so what is the simplest example of resurgence? Perhaps the simplest realization occurs in the saddle point evaluation of one-dimensional integrals. So let's suppose that you have a function here, for example, it could be a cubic function, and you want to calculate exponential integrals of this form in which you have this function wx divided by h bar. So the first step in resurgence will be to get a collection of formal power series that you can use as building blocks for your trans series. And the best way to do this in this example is just simply to do formal Gaussian integration around critical points. And in this way, you will get a family of formal power series attached to the critical points, which are factorially divergent in the formal coupling constant h bar. And there will be exponentially small terms involving the value of the potential at the different critical points. Now, the first thing you could ask is, what is the resurgent structure of this formal power series? What is the structure of the plane, of the Borel plane, and what kind of singularities you find? A very interesting result you can find here is that if you, for example, focus on this critical point and you look at the resurgent structure of this perturbative series around this critical point, you will find in the Borel plane other critical points. You will find the formal power series attached to other critical points. So, for example, in this case, in which you have a cubic potential, you will find a Borel singularity in the Borel plane. And when you look at the formal power series attached to the singularity, you will find the formal power series that you would obtain by expanding around a different critical point. So a given saddle point sees other saddle points, and this is one of the main characteristics of resurgence. You can explore the set of non-perturbative sectors of your theory by standing at a given critical point and then looking at what you find in the resurgent structure. And the location of the singularity is actually given just by the difference of the actions, if you want, between the critical point that you see and the critical point where you stand. Now, another thing that you want to do in resurgence is also to calculate exact quantities. And here, the typical quantity that you would like to calculate would be the integration of this exponential integral on a contour which is given by, for example, a linear combination of steepest descent paths. So this is going to be a convergent integral, and it turns out that it's given exactly, not just asymptotically, by the Borel-Ekal resumation of this collection of formal power series that we talked before, and the coefficients that appear here are just the coefficients that appear when you decompose your integration path in steepest descent paths. So this is a very simple example, and in a sense, one thing that you can try to do is to see at which extent in actual quantum theories this picture is true or not. So in order to explore that, let me actually first tell you what are the uses of resurgence in physics, because this is a very beautiful mathematical framework, but how you would apply resurgence in physics. There are two main applications of this framework to physics. The first one is to actually find non-perturbative effects by looking at the resurgent structure of perturbative series. So in principle, one of the kind of assumptions of resurgence is that you give me a perturbative series and you look at this resurgent structure, you will find other non-perturbative sectors of the theory. For example, in the case of saddle points, we saw that one saddle point can see other saddle points. And the additional series that you obtain in this way by looking at the singularities will be building blocks in the construction of trans-series. And the second application of resurgence is to use it to find non-perturbative definitions. So the conjecture or the hypothesis, the working hypothesis, that you can reconstruct physical observables by doing Borel-Ekal resumation of appropriate trans-series. Okay. So these are, in a sense, the main goals that you can set yourself in order to apply resurgence to physical models. Now, there are three very important caveats and three limitations of this framework, which I would like to emphasize. The first one is more practical. You see, in order to do resurgence, you really need a big control of perturbation theory. For example, you want to understand the resurgent structure of perturbative series, you really have to have, for example, an understanding of the perturbative series in detail or access to long perturbative series. And this is not always the case. For example, in realistic quantum field theories like QCD, we often have only 5 or 6 loops, and this might not be enough to do a very detailed resurgent analysis. Now, the second limitation is more conceptual, is that not all non-perturbative sectors appear in the resurgent structure of a given perturbative series. So sometimes people say that in resurgence, given the perturbative series, you get everything. This is actually not the case. Sometimes you need additional information to get the most general transseries. And the third caveat is that Borel-Lecal resummation does not give unique answers. Remember that in the transseries, I have to specify a series of coefficients which are these transseries parameters. So Borel-Lecal resummation gives you a family of non-perturbative completions parameterized by these transseries parameters, and sometimes you will need additional non-perturbative input to be able to find the actual non-perturbative definition of your observable. Okay? So these are 3 important caveats for the theory. Okay, now let me jump and discuss resurgence in quantum field theory. Of course, this is a complicated framework, and in a sense, in order to apply it to quantum field theory, we would like to have the simplest possible example of quantum field theory. And the example that I will tell you is perhaps not a conventional quantum field theory, but it's a theory that we, in string theory, we like very much, and this is Chern-Simons theory. Chern-Simons theory is, in a sense, the simplest example of the application of resurgence in the case of quantum field theory. So the Chern-Simons theory has appeared many times in this conference. Let me summarize a little bit how you define it. This is a topological quantum field theory for a G connection A on a 3-manifold M with this axiom here. And the observable I will focus in is the partition function of the theory on a 3-manifold M, which is given by a formal path integral of this theory, and I will denote the coupling constant by the letter tau. And perhaps the most important result in the concept of Chern-Simons theory is that if G is a compact gauge group and tau is of the form 1 over k, with k is an integer, there is a precise non-perturbative definition that Witten gave in his original paper. Now, what is less understood is the analytic continuation of this partition function to arbitrary complex values of the coupling and the construction for complex groups, and this is where we will see that resurgence can give us some interesting hints. Now, in contrast to realistic quantum field theories, the resurgent structures in Chern-Simons theory can be understood in detail. And one very interesting aspect of Chern-Simons theory is that also it's a topological quantum field theory has very non-trivial perturbative series. And it turns out that, in a sense, this is the natural generalization in quantum field theory of the kind of structures that you find in simple examples like one-dimensional integrals. And here, for concreteness, I will focus on examples in which the gauge group is SU2, and because this is actually where most of the results have been obtained. Now, as in the case of exponential integrals, what we would need is a collection of formal power series, and this, as in the case of one-dimensional integrals, will be obtained by expanding the path integral around saddle points. But there is already one important subtlety here. Even if you start with the gauge group SU2, we will have to really look at the complexified theory, so we will have to look at the expansion of the path integral around SL2C flat connections, and we will see in a moment 2 reasons why this is the case. And this formal power series, in many cases, they can be calculated systematically. There have been many techniques developed to do this, and we saw actually some examples in the talk by Mauricio. So what you obtain in this way is a collection of formal power series around SL2C flat connections, which are factorially divergent in general in the coupling constant tau. You will have an exponential prefactor involving the Chern-Simons action divided by the coupling constant. And in the simplest case, in which the space of flat SL2C connections is a discrete set, what you will find is a set of SU2 connections. In particular, you will have the trivial SU2 connections, which I will denote by 0. And then you will have genuinely complex connections. And a very important example is the case in which your manifold is hyperbolic. In this case, you will have 2 special connections, which are the geometric and the complex geometric connections, which are such that the real part of the Chern-Simons action is going to give you the hyperbolic volume of the manifold. And this is something that people use in Chern-Simons theory to study 3D gravity know very well. So what we would like to have is an understanding of the resurgent structures of these formal power series to see what they teach us about the structure of Chern-Simons theory. Now, there is an example in which a lot of information is known, and this is the case in which M, the three-manifold M, is the complement of a hyperbolic knot in the three-sphere. And this is actually the same setting that Mauricio was using in his talk. So I'm going to give you an example, and then I will see how this example generalizes. So I'm going to take the simplest hyperbolic knot, which is the figure 8 knot, and I'm going to take the simplest formal perturbative series, which is the one that you do by expanding around the trivial SU2 connection. Okay? So what is the resurgent structure that you find? This is a complicated problem, but in this case, it can be understood completely, and the answer here is in this diagram here. So this is the resurgent structure of this series, and what you find is that the Borel singularities form two infinite towers of singularities in the Borel plane, and the reason that we have towers of singularities here, which are separated by multiples of 2 pi I, is due to the multivalueness of the Chern-Simons axiom. And this is, in a sense, specific to Chern-Simons. Now, remember that attached to each singularity, we will have two pieces of information, another formal power series and Stokes constants. Now, the full tower here in this example gives you the geometric connection. The formal power series attached to these points is the geometric connection, the expansion of the Chern-Simons theory and the geometric connection on this hyperbolic three-manifold. And you see, this trivial connection sees other connection, in this case, sees the geometric connection, and this is a complex connection. So this is actually one of the reasons why we have to extend our point of view from SU2 to SL2C. This is forced on us by resurgence. Even if we wanted to start by restricting ourselves to SU2 connections, resurgence forces us to consider complexified connections. So here we have, in all these singularities, we have the formal power series attached to the geometric connection, and here we have the formal power series attached to the complexified geometric connection. And this is actually a general conjecture for all these manifolds that the trivial SU2 connection always sees the geometric connection, and in particular the location of these singularities, the real part of the location is actually the volume of the hyperbolic manifold. And for those of you who are familiar with this topic, this is what we call sometimes the resurgent version of the volume conjecture. The trivial SU2 connection always sees the volume of the hyperbolic manifold. Now, let me know also that let me know that here I actually put some numbers attached to these singularities. So these numbers are actually the Stokes constants, and also the formal power series attached to these singularities is always the same. The numbers are different. The Stokes constants are two infinite series of non-trivial integers attached to these singularities, and this is actually a very general fact that Stokes constants in this example of Chern-Simons series turn out to be integers, which can be explicitly computed or conjectured for many hyperbolic knots. And these integers, when you see an integer, you always have to suspect some sort of enumerative meaning, and this is actually the case here. There are two very nice interpretations for the integers appearing here. One is geometric. You could think about them as counting solutions to 4D flow equations with appropriate boundary conditions, which were proposed by Witten. And another interpretation is very different, and is based on the 3D correspondence that Mauricio was reminded this morning. So this 3D correspondence says to each of these hyperbolic knots, you can construct a three-dimensional supersymmetric theory, and it turns out that some of the Stokes constants, which are integers, which you find this resurging structure, are actually counting BPS states in this supersymmetric theory. And some of these Stokes constants agree with the 3D index for these 3D theories. And this is highly non-trivial conjecture, and there has been some recent progress by mathematicians toward establishing these conjectures. And this is something that we will see more appearance of this phenomenon. Let me first point out that also I have focused so far on hyperbolic knots, on complements of hyperbolic knots. There is also recent evidence that a similar picture also holds for closed hyperbolic three manifolds. So what is also happening in this example is that the trivial connection sees the geometric connection, you see the volume, and in particular, some of the Stokes constants corresponds to a closed version of the 3D index. Okay? So let me actually summarize a little bit this by pointing out a very interesting relationship. Here we have a quantum theory, which is a complexified Chern-Simons theory. Through perturbation theory, you generate a collection of formal power series, and when you apply resurgence to this formal power series, you get the Stokes constants, which are actually computing a BPS spectrum. And this is the BPS spectrum of a three-dimensional supersymmetric theory related to the quantum theory, in this case by the 3D correspondence. And this is not an isolated case. We'll see more examples of this type of relationship in this talk. And this is, in a sense, the stringy twist of resurgence. This is not something that you find in generic examples of resurgence. This is to be typical for resurgence in the kind of theories that appear in the stringy ecosystem. Now, I told you also that with resurgence you can try to get exact results, and one way to see how exact results appear here is by thinking about them as exact versions of asymptotics. There is a very, it's a classical result in Chern-Simons theory, which is sometimes called the Witten's asymptotic conjecture, that you take the partition function on a three-manifold M, and you take values of k which are very large, you can actually find the asymptotics of this quantity as a sum over formal power series in which you sum over SU2 connections. So this is already a trans-series in this guy, and it turns out that in many examples it has been verified that you can get an exact result for the partition function by just doing a Borel-Lecal resummation of this trans-series, and also including, on top of the SU2 connections, complexified SL2C connections. So complexified SL2C connections can also appear by giving you exponentially small corrections to this exact result. And this is another reason why you have to complexify the theory. But this equation is actually very interesting. It's an equality, and on the right-hand side, we are doing lateral resummations of this formal power series for values of the coupling constant of the form 1 over k, which are the values for which this partition function is well defined non-perturbatively. But now you can start from this side of the equation, and actually, nothing prevents you from trying to move in the complex plane of the coupling constant. And then, you can move in the complex plane. You have to take into account the Stokes discontinuities when you do that. And actually, you can analytically continue the right-hand side to the full complex plane of the coupling constant. And in many examples, have been shown that you can do this for the full complex plane, except for the ray along the negative axis. Okay? So this is the way in which resurgence and Borel-Lecal resummation allows you to do analytic continuation in complex Chern-Simons theory. Now, let me mention that resurgence has also played a very important role in the Gukov-Putrov-Pei-Baffa invariance of three manifolds and the Gukov-Manolescu invariance of knots K. These are Q series with integer coefficients, in which Q here is given by e to the pi I tau, where tau is the coupling constant. So these are Q series with integer coefficients. And in many examples, it has been shown that this Q series can be actually also obtained by doing Borel-Lecal resummations of appropriate trans series. Now, in the general case, it's not so much clear how these Q series invariants are related to Borel-Lecal resummation. In particular, in the hyperbolic case, it's less clear what is the relationship, and this is something that should be better understood. This is just to point you that the resurgence also plays a role in this different approach to analytic continuation of Chern-Simons theory. Okay, so in a sense, Chern-Simons theory is the simplest example of resurgence in quantum field theory, and the full structure of resurgence is determined by instantos. This is also what happens in quantum mechanics. But what happens in realistic quantum field theories? Now, the main message here is that in realistic quantum field theories, there is a source of trans-series which is in principle very different from saddle points. And I want to explain this here, and for this explanation, I will focus on asymptotically free theories. Okay, so let's suppose that you have an asymptotically free theory, and you want to calculate the vacuum expectation value of the product of two operators. So you can use the operator product expansion to calculate this vacuum expectation value. And when you do this, you will get two types of contributions. The first one is the contribution of the identity operator, and this is what you would obtain from the perturbative sector of the theory. And then you will get an infinite sum over all non-trivial operators of the theory involving the Wilson coefficients and the vacuum expectation value of these operators. Now, in asymptotically free theory, these vacuum expectation values are proportional to the dynamical scale of the theory to the power given by the dimension of the operators. But the dynamical scale of the theory is exponentially small in the coupling constant with a coefficient which is twice the absolute value of the first coefficient of the beta function. So the OP calculation gives you a trans-series, gives you a structure in which you will find a perturbative series plus exponentially small corrections. And actually, with a little bit of massage and going to momentum space, you get that this two-point function at momentum p is given by the perturbative series at the running coupling constant g at the momentum p, plus an infinite sum of terms involving a sum over operators, in which the role of factorial divergent series appearing in the Tar series is given by the Wilson coefficients in momentum space. You will have exponentially small corrections due to the appearance of the dynamical scale, and these coefficients here play the role of trans-series parameters. So in this context, the trans-series is given by the OPE, and the trans-series parameters are condensates of operators. And these numbers are supposed to encode genuine non-perturbative information about the ground state of the theory. But you have to take into account that, as in any trans-series calculations, they are going to be ambiguous due to Stokes discontinuity. So this is a subtlety that appears in the OPE, and this was emphasized by François David in the early 80s. So many terms in this trans-series should leave an imprint in the resurgent structure of the perturbative series. Perhaps not all of these coefficients, and actually not all of these terms in the trans-series of the OP leave an imprint, but some of them should leave it. And then you can actually deduce immediately what are the possible positions of the singularities in the Borel plane, because since here we have positions of, coefficients of this type, exponentials of this type, this is what determines the possible location of Borel singularities. So the possible location of Borel singularities are multiples of 1 over twice the absolute value of the first coefficient of the beta function. And this location of Borel singularities in perturbative series in asymptotically free theories are called infrared renormalons, and they were discovered and discussed by Parisi and Toft. So the most famous example of an infrared renormalon is the Adler function in QCD. So you take the 2-point function of the quark current, and this has a perturbative series, and it has been, these considerations led you to the conjecture that the first singularity in the Borel plane for the perturbative series of this quantity occurs at 4 times this quantity here, is due to the lambda to the 4 correction, and is due to the gluon operator in the OP. So this is actually a non-perturbative effect due to this gluon condensate. So I think this is a very important thing to emphasize, is that in asymptotically free theories, the first correction, the first non-perturbative correction to a perturbative series is not due to a saddle point. It's due to something with a slightly different origin. These are condensated renormalons, and they do not have an obvious saddle point interpretation. So in string theory, we rely very much on saddle point approaches to path integrals, including the gravitational path integrals, but I think it's sobering to remember that even in Yang-Mills and in asymptotic free theories in general, the first non-perturbative correction is not due to a saddle point. Now, I have been a little bit hand-waving in these arguments, but evidence for this picture can be obtained from many different sources. In actual QCD, people use large number of flavor methods in order to determine resurgent structures. And a very beautiful laboratory to understand this in detail is actually 2-dimensional models like Gros-Neve or the nonlinear sigma model, in which you can use exact large M methods to actually make this picture incredibly precise and verify all the details. Now, I have focused on observables which have an operator product expansion. So on observables which are obtained by doing the vacuum expectation value of the product of 2 operators, but there are observables with an OPE, like for example ground state energies, where you also find the same type of trans-series structure, and you also find this possible location of singularities which are renormalons. And in fact, the most detailed constructions of trans-series in asymptotically free quantum field theories, not relying on large N, occur in fact in a very specific observable, which is called the free energy coupled to a chemical potential H, that you can actually study in integrable 2D models. So by exploiting integrability, you can make this resurgent structure of observables very, very precise. And this observable, the free energy coupled to a chemical potential H, F and FH, denoted here by FH, was postulated by Polyakov and Bigman that could be calculated non-perturbatively by using the Bethe ansatz. And by exploiting integrability, you can actually write the precise trans-series that actually calculates this observable. So let me give you an example in a very well-known model, which is the O3 nonlinear sigma model. In this case, the full trans-series has been understood. So the full transeries of this observable starts, of course, with the perturbative part, and then you will have an infinite series of exponentially small corrections in which you have exponentials of this type, 1 over beta 0g. There are more terms here, and here you actually have two sources for non-perturbative corrections. You have renormalons, which have an ambiguous coefficient. Remember that the coefficients sometimes in this expansion are ambiguous due to the Stokes discontinuity. And then you have non-ambiguous instanton corrections, which here appear on the same footing, but in more general theories and more general observables, actually renormalon type of corrections are the leading corrections here. So there are, in my view, two main theoretical problems which remain unsolved in this picture. And the first one is very simple. Can we calculate from first principles the coefficients of these transeries? Can we calculate these condenses from first principles? And let me mention that, for example, in some rules in QCD, people use these transeries to actually calculate properties of hadrons, and the values of these coefficients, the values of these transeries parameters are extracted from data. Okay? But we would like to be able to calculate these condenses from first principles. Another interesting problem is that when your observables have no operator product expansion, like for example the free energies that I was telling you before, we do not even know how to calculate the transeries, the asymptotical series that appear in the transeries from first principles. We cannot calculate the analog of the Wilson coefficients for first principles. So these are very interesting problems. And of course, a radical way to solve these problems would be to postulate or to conjecture that all these renormalons or these condensate type of corrections are actually instantons in disguise. Okay? You could postulate that these actually have a semi-classical origin and they are instantons. And there have been proposals in this direction. Some of them are actually very interesting, but it's not clear to me whether you can use these proposals to actually do transeries calculations in realistic theories, even in two-dimensional models. Okay? So for the moment being, I think it's fair to say that we don't really have a semi-classical interpretation for these corrections. Now, let me point out that a more down-to-earth approach to this first problem of calculating these transeries parameters was made recently by Martin Benecke and Takaura. And the idea is that the only way we have to calculate non-perturbative observables in quantum theory reliably is the lattice. And you can actually remodel the OPE transeries in such a way that the ambiguous condenses that appear in the standard OPE are replaced by what are called Wilson flow condenses, which are calculable in the lattice. So in principle, you can change a little bit the structure of the OPE in such a way that all parameters are actually calculable from first principles, at least from lattice calculations. Now, I have so far focused on the coupling constant expansion in quantum field theory, but there are many other factorially divergent expansions that you can study with resurgence. In principle, any factorially divergent series can be studied with resurgence. So, and one of these expansions that for us is very important is the 1 over n expansion. The 1 over n expansion is actually doubly factorially divergent, and I will come back to this in a moment when I discuss resurgence in string theory. And in the case of matrix of the 1 over n expansion, resurgent aspects are well understood in matrix models and in very simple quantum field theories, but I think it's fair to say that in realistic quantum field theories, much less is known about the resurgent structure of the 1 over n expansion. Also, of course, in some special theories, like n equal 4 super Yang-Mills, you can actually make some interesting progress. Other series which are factorially divergent is, in some cases, strong coupling expansions, which appear in the context of ADS-CFT, that you can also understand with resurgence. And also the large charge expansion, which has been very much used recently, is also in principle factorially divergent, and you can also study it with resurgence. Okay, so let me come now to resurgence in string theory. So what is the main source of attention of resurgence in string theory? Well, most of the attention has been focused on the genus expansion in string theory. Now, you have a closed string expansion in string theory. It's going to give you a factorial divergent series in which the coefficients grow like 2g factorial. This has been known for a while. This is supposed to be a generic behavior in closed string theory. And elementary resurgent arguments then lead you to the existence of non-perturbative effects in the coupling constant of the form exponential of minus a over gs, where gs is the string coupling constant. And perhaps the most important breakthrough in the understanding of these non-perturbative effects was the proposal of Polchinski in 1994, who found a new source of non-perturbative corrections for these effects, which are D-branes. So from the point of view of resurgence, this idea of Polchinski has two very concrete implementations. The first one is that you can upgrade the genus expansion to a trans-series, and in order to do that, you will have to add D-brane amplitudes. And the second idea is that you should find in the resurgent structure of the genus expansion D-brane objects. And these expectations have been made quantitatively precise in low-dimensional models. So let me give you some summary of this. Now, one very nice laboratory to study this problem is the case of non-critical strings. And the reason is that in non-critical strings, the genus expansion is controlled by an ordinary differential equation, a nonlinear ODE. And actually, this is the best possible setting for resurgence, because it turns out that most of the mathematical studies of resurgence done by Jean et al. Were actually in the context of nonlinear ODEs. So by using the theory of nonlinear ODEs of et al., you can actually get a lot of understanding of resurgence in non-critical strings. So it turns out that the D-brane sectors that appear in the trans-series structure, the D-brane sectors can be simply described by using what are called trans-series solutions to this nonlinear ODE. So let me give you a very simple example, which is minimal 2D gravity. Minimal 2D gravity is described by the Painlevé-1 equation. And if you use a perturbative ansatz to solve this equation, you will get an infinite series where you can compute all the coefficients, and this gives you the genus expansion of minimal 2D gravity. But now what you can try to do is to solve this Painlevé-1 equation with what is called a trans-series ansatz. You impose that this solution will have exponentially small corrections, and actually the whole non-perturbative correction is determined up to the value of the trans-series parameter. You can actually determine completely, for example, the strength of the exponential term and all the terms that appear in the correction, and this turns out to be due to assessed brane. So in the case of non-critical strings, implementing this trans-series approach at the level of nonlinear ODEs is relatively straightforward. And of course, much recent progress to reproduce these effects from Walshit and strain field theory methods have been made even recently, as we saw in the talk by Ashok Sen. Now, there is another situation in which we have a great control of genus perturbation theory, and this is when the genus expansion is controlled by topological recursion. So this applies not only to minimal strings, but to other models, like, for example, JT gravity, and we saw today in the talk by Victor that you can also apply to C-equivalent strings and to other models. So when you have topological recursion on a spectral curve, you can also incorporate these trans-series extensions by doing what is called a non-perturbative version of topological recursion. So if you think about topological recursion as an abstract version of the loop equations of a matrix model, you can think about this non-perturbative version of topological recursion as an abstract version of the whole idea of eigenvalue tunneling that was put forward by David and Schenker. So if you have this applies in particular to spectral curves which have a pinching. And one beautiful aspect of resurgence applies in theories with topological recursion is that there is a universal description of the type of Borel singularities that you can find in the genus expansion. So Borel singularities are actually located at integral periods of the spectral curve. So the spectral curve is described by a function y over x, and this is the meromorphic function that you use in topological recursion. It turns out that the possible location of Borel singularities are just integral periods of this meromorphic differential. And this actually not only applies to non-critical strings, but it also applies to topological strings, which can be described with topological recursion. So these ideas then in low-dimensional strings are relatively easy to implement. Now, a more complicated case is the resurgent realization of D-branes in topological strings and tied to strings on Calabi-Yau manifolds. So I'm not going to tell you very much about this because this was the topic of my talk on strings in 2024, but I would like to emphasize that the resulting picture that you get from this is very similar to what we found in Chern-Simons theory. Namely, you have a quantum theory, which is a topological string, And then you can actually find perturbative series and also trans-series by doing actually a trans-series solution to the holomorphic anomaly equations of Versace, Ceccotti, Oguri, and Baffa. And actually, this is very similar to these trans-series solutions to nonlinear ODEs. And then you can apply resurgence to this set of perturbative series, and it turns out that the Stokes constant actually compute D-brane multiplicities. So by doing resurgence in this quantum theory, you get the BPS spectrum of a supersymmetric theory, which is related to the topological string. And there has been actual recent progress in computations of realistic calculations of D-brane BPS invariance with Stokes constants in papers, in very recent papers. So this is a conjecture that seems now to be established by, at least in examples, by actual calculations. Now, let me mention that also most of the applications that I have made here refer to the genus expansion. Any factorial divergence series can be studied with resurgence, and one of these series is the alpha prime expansion. The alpha prime expansion can be factorial divergent in some cases, and there have been also recent studies of the alpha prime expansion by using resurgence theory. Now, I'm almost done. Let me actually mention a final caveat for resurgence. So resurgence was, in a sense, invented to tame factorial divergences appearing in perturbation theory. But the problem is that the divergences you throw out of the window come out through the door. And it turns out that resurgence solves the problem of, in order to solve the problem of factorial divergence of perturbation theory, it has to introduce trans-series. And trans-series can be infinite series, which can come also with a new source of infinities. Trans-series in general involve an infinite sum of sectors, and this can, like for example in the OP, and this can introduce a new source of divergences. So the series of trans-series, so the sum over all possible sectors in the trans-series, is sometimes convergent. And for example, in the case of ODEs, it has been shown that the trans-series are convergent, but it has been argued that the sum over all these sectors appearing in resurgence might be diverging in other situations. So in the case of the OPE, there is a very beautiful argument by Schiffman that says that if you have a kind of a meson type of a spectrum, like linear spectrum of mesons in the theory, then the OP is going to be divergent. And all these exponentially small corrections that appear in the OPE are going to grow factorially. And this implies, by resurgence, that you should have doubly factorial corrections to this OPE expansion. Okay? So this is a new source of infinities and a new source of corrections. And another case, which is in a sense similar, occurs in type 2 strings, and this was pointed out by Boris Piolin and Stefan Van Doren. And the reason is very similar. You have, remember that the Stokes constants are given by D-brane multiplicities, so when the D-brane charge scales like n, you expect this Stokes constant to scale like e to the n squared. But if you have a series of D-brane corrections in which the coefficients grow like e to the n squared, you will have a divergent series which will induce a new type of ambiguity, and this ambiguity will be of the form e to the minus 1 over gs squared. So this could explain, for example, the appearance of NSF5 brane corrections, but of course, there is a new source of infinities that you have to tame again, right? So you will have to do another layer of resurgence in order to tame these singularities. But you see, these are both appearing in this trans-series expansion in string theory and also in the standard OP expansion in asymptotically free theories. So this has not been really much explored, but it's clearly an important issue in my view. Okay, so let me come to the conclusions. I think it's fair to say that the theory of resurgence gives a very interesting framework to understand non-perturbative effects in a variety of quantum theories, and it also gives us a way to upgrade perturbative series to exact answers in many examples. It has had many successes and applications. A very clear success is the exact WKB method, but also OP methods in quantum field theory are eventually based on trans-series. And I would, since this is a string theory conference, I would like to mention that there is a stringy twist to resurgence that appears in all these examples in which the Stokes constant seems to be calculating BPS spectra. And let me actually emphasize this. So the picture that appears, the stringy twist to resurgence, it seems to be the fact that in some cases a supersymmetric theory is related to a quantum theory, and the structure of perturbative series in this quantum theory can be worked out in detail. Its resurgent structure through the Stokes constants gives you BPS spectra of the supersymmetric theory. So we have seen two examples in this talk, Chern-Simons theory and 3D n=2 theories, topological strings and two-type 2 strings. But there is even a simpler example that I didn't have time to explain, and this is the supersymmetric theories in n=2 supersymmetric theories in 4 dimensions. And in this case, the quantum theory is very simple. It's just quantum mechanics on the Seiberg-Witten curve. And by doing resurgence in this quantum Seiberg-Witten curve, you actually get the spectrum of the supersymmetric theory. So this is related, of course, to all the work starting actually with the work of Kuhn, Rung, and collaborators on geodesic cycles, on Seiberg-Witten curves, and all the developments on wall crossing and so on. But from the point of view of resurgence, you could express it in this way. Now, in its current form, resurgence has many limitations, and I have tried to emphasize the caveats. We cannot use just a perturbative series to get access to all non-perturbative sectors. This is not known to be the case. For example, instantons in the O3 nonlinear sigma model cannot get access from the perturbative series. This has been known for a long time. There are other technical problems, like, for example, how to calculate the Stokes constants analytically. We don't know how to do it in general. The potential new divergence that appear in the resummation of the trans-series have to be treated in more detail and probably require a higher level resurgence analysis. And there are, of course, there is room for improvement in quantum field theory and string theory. And there are, in particular, other areas where resurgence has made a small impact, but we are far from having a more complete theory. And one important area where I think resurgence will be developed more is in the context of quantum chaotic systems. What we would like to have is, in a sense, a version of exact WKB for quantum chaotic systems, some sort of exact theory of a periodic orbit expansion. And this is not really available. There are some resurgent results in that area due to, in particular, Michael Berry. We are far from having a complete theory, and this is an area where I think we could have a lot of improvement, and of course, it would be very interesting to string theory. Okay, let me thank you for your attention.
Hi, thank you, Marcos, for the beautiful talk. Any questions?
Thanks for the nice review. I have two questions. One, maybe it's a bit specific, but I was a little bit confused when you said the trans-series parameters, the C, are choices. But then you, for instance, give us an example of SL2C Chern-Simons theory, and you wrote an equality. Does that mean those C's are some numbers, specific numbers? Or?
No, when I mean they are choices, I mean there are various things here. First thing is that if you are giving just the general structure of a trans-series, you have to fix the trans-series parameters, and very often you need some sort of non-perturbative information. Okay? That's one thing. Now, then there is the question of Stokes discontinuities. It's true that, this Stokes constant, this has created a lot of confusion, in particular in the case of the OP. There was a big debate on this, but now we understand that these coefficients are defined up to jumps by Stokes constant. So depending on your choice of lateral resummation for the formally divergent series that appear, in particular for the perturbative sector, the trans-series coefficient will have one value or another depending on that. So, for example, here, in a sample I gave you before, let me see if I get there. Here, for example, in the O3 nonlinear sigma model, you see this non-perturbative correction has plus or minus I, and the choice of plus or minus depends on how you decide to resum the perturbative part. If you decide to sum with lateral resummation up or down, you will have to choose plus or minus I in order to get actually a non-ambiguous answer. So the ambiguity in the coefficients is there to guarantee a non-ambiguous answer at the end of the day. Okay? And also the fact that you have here a plus or minus I doesn't mean that there is some sort of decay or something like that. This is actually required for having a real answer, because the lateral resummations of this series will give you an imaginary piece which you have to cancel with this Stokes constant here. Okay? So that's the main thing. I don't know if this answers your question.
I think so. Yeah.
Okay.
And the second question was another situation. We have a nice OP is CFT that has then been. Has there been much work?
I have to say that I haven't thought too much about OPs, but I think In the case of OPs, if I understand correctly, Slava, I don't know, he's maybe around, he could tell us in detail. I think in the case of CFTs, the OP is convergence, so this is a very different situation, as far as I understand, okay? I really focus, my understanding is really for asymptotically free theories. I have not tried to understand this in conformal field theories.
Right, thanks.
Very nice talk, Marcus. Good, nice review. So one thing which appeared in various examples was that some saddles which don't seem to naively appear in the path integral. For example, in the SU2 Chern-Simons, you pointed out the flat SL2C connections also appear, which is surprising. Now, this also reminds me of the fortuitous states when people are computing these indices. Supergroups come in, which is, again, not expected. Sounds like a non-unitary one. First of all, do you have any interpretation of these non-unitary, appearance of these non-unitary kind of context in a theory which is unitary, and why is it important for the non-perturbed one in the easier case of Chern-Simon, and whether there's a parallel, do you see in the black hole count in those fortuitous states?
Yeah, I mean, let me first point out that this is not specific. This already appears in quantum mechanics. So in quantum mechanics, very often you have to include complex saddles in order to have real answers. I think this is part of the structure of resources, that you have to include these saddles there. If you have some sort of picture, clear picture of paths in the path integral, you would probably be able to derive this from first principles, because it's also in the saddle point. You have, in the saddle point method, you also have to look at these complexified saddle points, right? So I think these are pointing out to some deep facts about the space of paths that you have to consider in the space of path integrals. But this is all the understanding I have about this. But let me just emphasize that this is really also happens in very elementary examples.
I have a question about the I have a question about the one-of-n expansion. The trend series in one-of-n expansion.
Yes.
I think one thing very different from the coupling constant is that n is discrete. So suppose at finite n, I only know the integer value of the functions, and I have no idea about the NA continuation. Is there any way I can extract the trend series in the larger limit, or I really need to know the NA continuation?
No, I would say that in principle you just have only the finite n values. There are infinitely many interpolating functions that you could have, right? So you have to have access to some type of perturbative structure that tells you that you can use as a starting point for an analytic determination of the interpolating function. But usually perturbation theory comes with an explicit independence that you can use to do this interpolation.
Professor Witten.
Yeah, well, Shankar's argument predicting that in string theory there should be e to the -1 over g effects would seem to apply also to the heterotic string, which doesn't have d-branes. Is there any understanding of what might be those effects in the heterotic string?
I haven't thought about the case of the heterotic string, so yeah, I cannot tell you what would be the object there that would play this role. Yeah.
So in your presentation, you give impression that in the case of topological string, Lisa mentioned it's well understood. But in order to do that, you need to have a good control of perturbative expansion.
Yes.
So I'd like to ask you again. So in the case of compact Calabi-Yau manifold, where finding asymptotically large the partition function for asymptotically large genus, there are still challenges. What kind of information can you extract in such a case?
Yeah, let me first point out that there are two different problems in resurgence. One is the determination of resurgent structures, which is is a well-defined problem with a unique answer. So if you give me a perturbative series, what is the resurgent structure? Up to very kind of general assumptions, it's a very, it's a unique...
But when you say given perturbative series, do you need to know to the all genus, for example?
Yes, yes, but there are techniques to actually approximate, the resurgent structure, giving a finite truncation of the series, and this is what people have done. Let me say that, first of all, for compact Calabi-Yau manifolds, there are analytic results of, for example, the trans-series attached to the singularities. This is completely understood analytically, and you can, for example, derive the wall-crossing structure of the topological string up to Stokes constants. The only thing which is not known at this stage are the Stokes constants. And the Stokes constants can be determined numerically in an approximate way, even if you have a truncated series. So there are techniques to do that. And in some cases, one can actually check that the degeneracies that are obtained numerically agree with the VPS multiplicities that people have obtained with other means. I wouldn't recommend this as a way to compute the brain multiplicities in general. I think there are methods which are much better. But from the point of view of the resurging structure, it seems clear that the Stokes constants are actually computing VPS multiplicities. And this is the only thing which is undetermined in the resurging structure. The values, the numerical values of the Stokes constants. Everything else is completely determined. In particular, the form of the exponentially small corrections.
Thank you.
Yeah, I'm confused about something very basic in this whole program, and I think I'm missing some assumptions. So at the beginning of your talk, you gave the example of a single integral with a cubic potential, and you said that the perturbative expansion around one saddle knows about the other saddle. But clearly for all potentials, that can't possibly be the case because there's potentials that have the same germ around your given saddle, but have whatever other whatever other saddles you want.
Yeah, this is a generic statement. When I say that the perturbative series sees that one saddle sees other saddles, this is a generic statement. It's not, for example, it's known that a saddle is not going to see all other saddles. That's also, for example, happens in Chern-Simons theory. If you start with the geometric connection, you will never see the trivial connection. So this is a generic statement. I'm not saying that a given saddle sees all other saddles. See that in general, one saddle will see other saddles.
I guess I don't understand how that can be the case, because what if your function does not have that other saddle that you think it sees?
What? Yeah, but this, as I said, this is a generic statement. There can be, for example, there are cases in which we don't even have a perturbative expansion. So you cannot even, so for example, there are problems in quantum mechanics in which the perturbative series is exactly zero. So, there is a non-generic case in which the perturbative series vanishes at all orders, and then you will not see other saddles. So that's my generic, that's a generic statement. What I'm making is a generic statement.
Just a comment. I think implicitly you're assuming real analytic potentials.
Yes.
So that the last question can't really arise.
Thank you.
But you can have multi-valued potentials, like, for example, in Chern-Simons theory, in which you have also an understanding of these saddles in that way.
So just a comment, I think, related to Edward's previous question about the heterotic string and this thing. Indeed, Polchinski suggested that heterotic string can also have boundaries for non-perturbative ones, for SO32 in particular. So that is consistent with this e to the 1 over g expectation.
Yeah, hi. Thanks for a great talk. So I'm wondering about two further potential applications in string theory. So one would be actually to M theory, where people try to engineer a perturbation series by having a circle, so Michael Green and collaborators, and trying to compute in a perturbation expansion in M theory and so on. Do you know if you can apply this program in this case and whether you can learn something?
I mean, you need a perturbative series as a starting point, right?
That's the perturbative series. So the perturbative series is in 1 over r, where r is the radius of a compactification circle to 10 dimensions. And you compute, you have to fix coefficients, which you fix by using dualities to type 2A theory and so on. But so you know some terms in the perturbation expansion. As you emphasize, in most cases, you only know a very small number of terms, and in this case, that's the case. But perhaps, so in addition to looking at the perturbation expansion in the loop parameter and in alpha prime, one could try and look at this one. Whether one learns something else, I don't know.
Yeah, absolutely. I mean, the problem of resurgence, in a sense, is a very generic method. It applies to, it's very generic. It's very, the skeleton of the theory is very thin because it's very generic. So if you have a factorially divergent series, you can always apply this method. So of course, you have to make sure that your series is factorially divergent. That's the only assumption.
Yeah, and another potential application would be n equals 8 supergravity in 4 dimensions. Again, you know very little, but you might know some terms or you have some information about a few loops, and then, perhaps one can learn something for the rest of the theory.
Yeah, okay.
Thank you.
All right, so thank you all for coming to this morning's sections, and as I resume after lunch at 1:30. Thank you.
do some research.
Thank you very much.
Yeah. I'm also working as a professor, but Melanie, been working on hierarchy manuscript, but yeah. Yeah, yeah. Well, I don't know. Yeah, it seems to be working. Yeah.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Hello?
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay. Welcome back to our afternoon session. So the first speaker is Professor Slava Rychkov from IHS. So he's gonna talk about the experimental test of conformal invariance in critical phenomena. So welcome.
Thank you. Thanks for putting together this great conference, and thanks for inviting me. So since string theory owes so much to conformal field theory, and vice versa, I thought that you might be interested to know something about the experimental status of conformal invariance. And a priori, you would think that conformal invariance should be in good shape because it is, after all, believed to be a symmetry of critical fluctuations, as famously proposed by Polyakov more than 50 years ago. And of course, critical phenomena are all around us in nature. And so what this means is that if you look at the probability distribution of the critical fluctuations of the order parameter, and if you apply a conformal transformation, then this probability distribution should remain invariant. And of course, that's something that people see in Monte Carlo simulations, both in 2 dimensions and in 3 dimensions. But can we say that this has also been seen experimentally in a lab? So as you will see, the answer is yes. But in some sense, it would be nice to have more direct, more explicit tests. And so today I'm going to describe some proposals for such tests. So for the purposes of this talk, I'm going to divide tests of conformality into direct tests and indirect tests. So symmetry is fundamentally about shapes of objects. And in quantum field theory, our objects are correlation functions. So direct tests are those which test conformal word identities for correlation functions. That's clear. On the other hand, conformal field theory also makes very non-trivial predictions for, say, scaling dimensions of operators, which determine critical exponents. And those critical exponents can be experimentally measured. And so every time there is an agreement between this experimental measurement and a prediction of CFT, we will say that this is an indirect test of conformal invariance. And actually, over the last 50 years, there has been many hundreds or maybe thousands of experimental measurements of critical exponents. And most of them, a great majority of them, is actually in agreement with conformal field theory. So in this sense, you can say that conformal field theory passed a great many indirect tests. And so here I'm just giving two experiments. So one experiment which measures the critical exponents of the two-dimensional Ising model. This is a two-dimensional ferromagnet. And another experiment which measures the critical exponents of the three-dimensional O2 Wilson-Fisher. So this is the famous liquid helium space shuttle experiment. But when I started looking at the literature, I was actually surprised to discover that the direct tests, as I define them, are currently lacking. So this is a shame. And so today I would like to propose a few such tests, which I consider relatively realistic. And realistic is really the key challenge here, because we don't want to just dunk an experiment or a thought experiment. We really want an experiment which can be done in a lab today or tomorrow with existing experimental technology. And so this is the first test, which I worked out with Alessandro Podo, one of our postdocs at IHS. And so this is our proposal in a nutshell. We are going to look at the two-point function, at the critical two-point function of the order parameter, and we are going to look at it in a half space. So this is really a classical criticality, find the temperature, think liquid vapor phase transition, or paramagnet ferromagnet transition, or binary LA, you name it. Let's just take Ising universality class for simplicity. And I'm looking at it in half space. So there is really a flat boundary. This is boundary CST setup. And I'm going to probe this two-point function by scattering X-rays or neutrons in the regime of the so-called grazing scattering. I'm going to explain what it is. And there's going to be a scattering rate, there's going to be a cross-section, which is going to be as a function of the momentum transfer and scattering angles. And I'm going to express the constraint of conformal invariance as a certain differential operator acting on the scattering rate. And so if you act with this differential operator, and if you get 0, well, that's going to be a direct test of conformal invariance. So let me explain the rationale between various choices. So first of all, why the two-point function? Well, because when you scatter an X-ray or a neutron of the critical sample, then the scattering amplitude is proportional to the Fourier transform of the instantaneous distribution of the order parameter. And when you square it to get the rate, and if you average over many scattering events, you get the Fourier transform of the two-point function. And then, of course, at criticality, the two-point function is a power of the distance. It's 1 over r to the power 2 delta O, the scaling dimension of the order parameter. You Fourier transform it, you get the scattering rate, which is 1 over q to the complementary power d minus 2 delta O. So that's actually very well established, and that's how you determine the dimension of the order parameter experimentally. So we could use this, but there is a problem, that this measurement, it doesn't test conformal invariance. It only tests scale invariance. Because scale invariance by itself is already enough to say that the two-point function is the power of the distance. So that's why we go to the half space. So this is the half space. We have a flat boundary. We have the direction orthogonal to the boundary. There are 2 points. The distance r between them. The distances to the boundary. And so in this setup, it was realized by Cardi long ago. The conformal invariance actually does constrain the two-point function. So the two-point function is now 1 over r to the 2 delta times a function of a cross ratio. So this is a boundary cross ratio, r squared over zz prime. Of course, as usual, conformal kinematics alone does not tell you what this function g of xi is. You can do conformal bootstrap, and actually there were many studies about this, and this function is rather well known, thanks to these studies. But that's not my point here today. What I want to stress is that if you only had scale invariance instead of conformal invariance, then instead of one cross ratio, you would have two cross ratios. And so in this case, really, conformal invariance does give an extra constraint, and we would like to use it. Now, what is this grazing scattering, and why we need this? Well, because when you compute the scattering rate, you take the Fourier transform, there is a volume factor. And so this volume factor tells you that you are dominated by the bulk. But we want to be testing the behavior of the two-point function near the boundary. So what do you do? Well, there is this cute fact about X-ray optics, that X-rays, unlike the visible light, they have the refraction index less than 1, so a tiny bit less than 1. And so what this means is that if you take an X-ray and if you send it almost parallel to the boundary of the sample, so at an angle, incidence angle below some critical angle of a few degrees, then it's going to experience total reflection. And so this is called the grazing scattering. And so when you have the grazing scattering, the wave function of the X-ray decays exponentially into the bulk, and it probes the critical fluctuations near the boundary. So that's just what we want. Well, to be precise, the scattering rate is going to be a function of the momentum transfer along the boundary, Q, and a complex number kappa. So this complex number kappa is this function of the incidence angles of the incoming and the outgoing X-ray, alpha I and alpha F, and the critical angle alpha C. And so what is important about this formula is that if one of the two angles, alpha I and or alpha F, is smaller than alpha C, then kappa has a positive imaginary part, and in this Fourier Laplace transform of the half-space two-point function, which expresses the scattering rate, it exponentially decays into the bulk, and that's precisely what we want. But actually, we are going to be interested in the regime where one of the angles is below alpha C and another is above alpha C, because in this regime, kappa, this parameter kappa, has both imaginary part, which is positive, and it has a non-zero real part. And we are going to play with both this real and imaginary parts. And so next is the conformal word identity. So in position space, it's well known. So the conformal word identity for the two-point function is expressed by acting on it with this differential operator corresponding to the conformal generators. For example, the special conformal generator K mu. It's also known, at least in the infinite space, that you can take this conformal word identity and can Fourier transform it to momentum space. Now the gradient become powers of momentum and vice versa, so you get a differential equation, but now in momentum space. We are in the half space, but we can use exactly the same idea. You have to be a little bit careful about boundary terms and whatnot, but when you do the calculation, you find the conformal word identity for the grazing scattering rate, which is this second order differential equation which the scattering rate should satisfy. So you see it involves the derivatives with respect to momentum transfer along the boundary, and it also involves derivatives with respect to the real and imaginary part of this parameter kappa, complex parameter kappa, in some particular linear combination. And so this equation is our proposed test of conformal invariance. And it's very important that you formulate this test in momentum space, because experimentalists, they can measure this scattering rate in a range of momentum transfers and the scattering angles. So they would not be able to take this partial information and reconstruct the full position space two-point function and see that it has the Cardi form. But they definitely can apply this differential operator, and they can see whether they get zero or not. And this is a valid test of direct test of conformal invariance. And so what are the experimental prospects? Well, actually, the grazing scattering experiments for boundary critical phenomena were already done more than 30 years ago. And that's the kind of data that people measured. So this is the scattering rate as a function of the momentum transfer. So let me explain. You see that here they see kind of a cuspy behavior at small momenta. This happens because at small momenta, the scattering rate, it is a sum of a non-analytic piece and an analytic piece. And this non-analytic piece, it starts by q to the power 2 delta 1 hat minus 2, where delta 1 hat is the scaling dimension of the first boundary operator, which is about 1.3, so this exponent is about 0.6, and that's what they see here, because the coefficient n0 is negative. Now, all these other terms, the subleading terms, and the analytic pieces, their coefficients, they depend on phi. Phi is the phase of the parameter kappa. Remember I said that if alpha I is less than alpha critical and alpha f is larger than alpha critical, then kappa has both the real and an imaginary part, and so phi is non-zero. And so what happened in this old experiment is that they were after measuring this exponent delta 1 hat. So obviously they didn't know about our conformal word identity, so in order to improve the statistics, they integrated over phi. So you see their detector here, it integrates over the outgoing scattering angle alpha f, which effectively integrates over phi. And so this is why they have this plot which depends only on a single variable q. So unfortunately, we cannot use this published data in order to test our conformal word identity, but hopefully it's just enough to repeat this experiment without integrating in phi, and hopefully it can be done if it was already done 30 years ago, and this is going to give us a valid direct test of conformal invariance. So now let me shift gear a little bit and talk about a second experiment, possible experiment. So this is the work I'm doing with Junchen Rong, who is also in Paris. And by the way, I think he is on the job market in China, and I think he's really outstanding. I hope he gets a nice job. So let me explain what we are after. We take a bunch of cold Rydberg atoms. I'm going to explain what they are. We put them on a circle, and it's not, it's enough to get just a few dozens of these Rydberg atoms, and you prepare them in a critical ground state, say of the 1+1 dimensional Ising model. And then you flash a laser. When you do this, the wave function collapses, and you get a strings of zeros and ones, so which say whether the atom was in the ground state or in the excited state. Then you repeat this many times, you average, and then you can measure anything. You can measure 2-point function, 3-point function, 4-point function, whatever you want. It's really a powerful technique. You are just limited by statistics and by some decoherence effects. But let's just focus on the 2-point function. So theoretically, what you're going to be measuring is a CFT 2-point function on a cylinder at equal cylinder time. And we know that this 2-point function has to be equal to 1 over sine of the half difference of the angles to the power 2 delta O. And so what I want to stress is that this finite volume 2-point function, it tests directly conformal invariance. So remember I said that in infinite volume, a power law, it was only testing scale invariance, but this 2-point function has a very peculiar dependence. Okay, at short distances it's a power law, but the fact that it has this form at finite angles, at angles differences of order 1, this is direct consequence of conformal invariance. So this is really a potential for a direct test. Okay, so this is just to remind you what Rydberg atoms are. So these are the two-level systems. There's a ground state, Rydberg state. Everything happens in the coherent field of a laser. There are Rabi oscillations, and there is some detuning parameter which prefers the Rydberg state. So these are these two parameters, omega and delta. And finally, there is this very rapidly decaying 1 over r to the 6 interaction, which activates when the two atoms are both in the Rydberg state. So if you stare at this Hamiltonian, you see that if you transform from the 0, 1 basis to the sigma z, This is just the Hamiltonian of the anti-ferromagnetic Ising model in a combination of transverse and longitudinal magnetic fields. And so this Hamiltonian has this sort of phase diagram which separates the phase, antiferromagnetic phase, where the Z2 symmetry translation by one lattice unit is broken, from the disordered phase, and there is this critical line, and every point on this critical line is 1 + 1 dimensional, is 2-dimensional Ising CFT. And actually, this has already been realized experimentally, so there are these recent papers by a Harvard group and by a Caltech group, which realized 2 points on this critical line. And in particular, this Harvard group, they realized precisely the setup that I described. So Rydberg atoms on a circle, they measured the 2-point correlation function. Unfortunately, instead of seeing the CFT dependence, they saw an exponential decay at distances, at large distances, which they attributed to decoherence effects. So the direct test is not there yet, but with Junchen, we believe that this can be optimized. Because the point of these experiments is that you prepare this critical ground state by performing adiabatic evolution, and you want your evolution to be as fast as possible in order to reduce decoherence, but not too fast, because it has to be adiabatic. And so we believe that by playing with this critical line, in particular, we like this point near the tip of the parabola, we can optimize the evolution time, and hopefully the decoherence can be reduced, so the direct test of this conformal invariance should emerge. So this is work in progress. Well, I have time for the last test of conformal invariance, which is probably my favorite, if it works. So it has to do with percolation. So percolation is a geometric transition. So it arises if you take, say, a square lattice, you pick some probability P, and you open or close every edge on the square lattice with probability P. So as you increase the probability, at some point you hit the critical probability P critical, at which this infinite percolating cluster emerges. So this is a phase transition, and this phase transition is conformal. So in fact, it is a logarithmic CFT, both in 2D and in 3D. And much is known about this phase transition theoretically, but what I want to stress today is that this phase transition is very important for coffee extraction. So if you compress your coffee powder too much, then the water doesn't go through. If you compress it too little, then the water goes through too easily, and you get watery coffee. So in fact, if you're a good barista, then you have to work at the percolation threshold. And so this brings me to this tantalizing possibility that perhaps we can test conformal invariance with an espresso machine. So I think if this is true, then this would be really the favorite theorist's test of conformal invariance. I'll stop here.
Okay, now it's question sessions. Any questions? Over there, there's a question, yeah.
Thank you for a nice talk. So in the first test, you implicitly assume that your X-rays or neutrons, they couple to a primary operator in the CFT. Is it an important assumption? Is it possible to relax it?
Yeah, you have to think about what the X-rays or neutrons couple to. So neutrons coupled to magnetic moment. If you're studying a magnetic transition, then typically they are going to couple to the lowest operator, to the lowest scaling dimension operator, which corresponds, which is charged under Z2 symmetry, which is primary, which is the sigma operator of the Ising CFT. If you study X-ray scattering, then typically you will be using X-ray scattering for transitions like binary alloys, where the fluctuating quantity is the electron density, and X-rays, they scatter on the electron density, so again, you couple to the sigma operator. So typically, you just couple to the sigma operator, which is the lowest dimension operator of your CFT, which is the primary.
Okay, any other questions? We do have time for a few questions. Yes? Over there.
It's sometimes claimed that scale invariance in fact implies conformal invariance. So what does a failure of these experiments mean? If you do not find conformal invariance, do you blame the theorist or the experimenter?
Well, scale invariance implies conformal invariance under certain assumptions which we believe to be generically satisfied. So, for example, for universality classes like two-dimensional Ising model or three-dimensional Ising model, those assumptions are satisfied. There are, of course, phase transitions in nature which realize scale invariance without conformal invariance. So if you apply these tests to those phase transitions, then presumably you will get negative results.
So still, what are you testing?
Physics is an experimental science. If you have a theorem, it still doesn't qualify as an experimental verification. I'm testing experimentally our most cherished theoretical assumptions. That's what I'm doing.
So in the first part, right, so I'm wondering that the fact that the sample is always finite, it has finite width, length, would that affect your analysis, let's say?
Not much, because as usual, you have to make sure that your sample is large enough so that the aperture of the incoming beam is smaller than the size of the sample. But this is not a very strict assumption. In fact, the angles we are dealing with are small, but they're not really minuscule. It's just a few degrees. So the finiteness of a sample is not a problem.
Yeah, but it's a gapless system, right? It's like correlation length is infinite, right? So.
Well, you just have to make sure that that your aperture of the beam is larger than the correlation length. The correlation length is never exactly infinite, right?
Okay.
Yeah.
Okay, any other questions?
So the fact that this percolation is log CFT, what would it mean practically, especially in your favorite test?
Well, in log CFT, nature of percolation is a subtle phenomenon that you see by observing some correlation functions of relatively high scaling dimension operators, like, for example, stress tensor, it has a log partner, and so on. If you look at the most standard observables of percolation, like, for example, the three-point function, which is the probability that the percolating cluster touches 3 points, this observable just satisfies the usual Polyakov three-point function formula. There's no subtlety there. There are no logarithms there. So to see the logarithmic nature of percolation, you really have to look at very subtle observables.
There's. It's coming. It's coming.
Thank you. Hi. So if I'm not mistaken, there have been experiments with, say, magnets or quantum Hall states that can show some confirmation of conformal invariance. I'm wondering, what is your, what do you hope that these experiments could teach us? Is it about some particular system, or do you have some, goal out there that you hope we would be able to somehow confirm with these experiments?
I'm not aware of the experiments with quantum Hall systems which confirmed conformal invariance. I would be interested to know more about those references.
Yeah, I'm not an expert myself. This is some thought I thought was true.
Yeah, what do you expect to learn about this? Experiment always lags behind theory, right? So a little bit. So you often you make an experiment, you discover the Higgs boson, and then everybody says, well, we always knew that the Higgs boson was there. So what did you discover? Well, you discovered that the Higgs boson was there. Sometimes it happens that by doing experiments, even on well theoretically understood systems, you discover some subtle effect that theorists overlooked or theorists didn't think about, or so we will see. When the experiment is done, we'll see if it works out, and we see what it tells us. So I think it's still important to do experiments. So I think conformal invariance is perhaps the only symmetry of nature for which I do not know of an existing direct experimental test. So I think this is a shame.
Okay, we have enough questions, so let's thank the speaker again. Yeah, let's welcome the next speaker.
Hello. Hello.
Okay. Our next speaker is Yang Zhou from Fudan University. So he's going to talk about the universal defect energy and the entropy from well anomalies. Thank you.
Thank you. Thank you so much. First of all, I would like to thank the scientific committee for this opportunity to speak. Also, as a local speaker, I would like to welcome all the friends to Shanghai. I'm Yang Zhou from Fudan University. Today, my title is Universal Defect Energy and Entropy from Wire Anomaly. This is based on a recent paper with two excellent students, Wang Zixiao and Yuan Ma Ke. Both are here. In particular, Wang Zixiao is seeking for postdoc positions this fall, so please pay attention. Also, based on some work in progress. So the motivation really comes from the real world. So in nature, it's really hard to find some perfect system. So usually we have some defect. So the question will be to explore structure independent of the microscopic realization of the defect, meaning we want to find some defect universality or universal structures. To be more precise, we can consider a 2D quantum system. So for some reason, along some line, there could be some irregular degrees of freedom. So it forms some, in space, it forms some line defect. So we are quantum field theorists, so we would like to consider this problem in quantum field theory context. So we'd like to take the continuum limit, so plus the time direction. This is actually give a surface defect in the system. So thanks to the previous talk, we don't need to explain. Actually, at a critical point, the problem becomes a defect conformal field theory. So if you ask me what is the definition of the defect in quantum field theory, this is possibly one. Defect can usually be defined by non-local operators or boundary conditions in quantum field theory. For this reason, defect can be classified by their dimensions, say a line defect, surface defect. For example, in gauge theory, there are well-known examples like Wilson line and Wilson surface. If you want to write down a simple example, say in free scalar theory, one can construct such a line defect by adding a term to the action addressed by a d-1 dimensional delta function. So this deformation term will give a defect localized at the origin, and there could be also a coupling constant gamma measure the strength for the defect coupling. So if you want to try to classify defects, it's really hard because there are a lot of different examples, but you can perhaps do the following. So the simplest defect you could imagine is the topological ones. Topological ones means the shape doesn't matter. So recently, these are the key tools to explore the so-called generalized symmetry. I believe this afternoon, Yifan is going to talk more about that. So the slightly non-trivial one, you can see some conformal defect. They are not topological, but still there are some symmetries. So they appear as the fixed point of the defect RG flow. There are also many different examples like monodromy defect, including the entangling surface. You can also view them as defect. So in general, to solve a defect in quantum field theory is pretty hard. So let's restrict ourselves to the conformal field theory, including the conformal defect. So in the presence of defect, the conformal symmetry is broken down to this part. So this essentially means if you're standing on the defect, there is still a small conformal symmetry, plus this rotation symmetry. So if you use the conformal symmetry together with conservation, you can actually fix the one-point function of the stress energy tensor in the presence of the defect up to a constant. Here, small h up to a constant. So all the other structures is basically fixed by the symmetry. So now we begin to ask the following question. Remind ourselves, in 2D conformal field theory, we often teach in the CFT course, there are two key results in the 2D CFT. One is the Casimir energy of the 2D CFT quantized on the circle. Then it's minus c over 12r. R is the radius of the circle. Another well-known result is the Rayleigh entropy of a single interval in 2D CFT, which is also fixed by the central charge C. And the other part is linear to 1 over n. Okay, there's log here. So these are two observables completely fixed by the central charge. Now we can ask the following question. Imagine if our system have a surface defect. So if you count in dimension, surface defect also has 2 dimensions. So there's also a small conformal symmetry. So the question will be, can we find some surface defect related observable also share the similar structure of the 2D CFT? Of course, the symmetry is not completely equivalent because 2D CFT has very thorough, but still there's a conformal symmetry. Can we find some observables for the surface defect? It's also fixed by, for example, the surface defect wire anomaly. That's the question we want to solve in this talk. So then, first we should clarify how to classify what do we mean by the anomaly, wire anomaly, a conformal anomaly for the surface defect. So for a surface defect, luckily, the wire anomaly is classified also. So analog to the wire anomaly in 2D CFT, but now we have 3 anomaly parameters. Okay, there's a B, there's a D1, and a D2. B is essentially the analog of the 2D CFT central charge. And there's also a D1, is a coefficient of the displacement operator 2-point function. There's also a D2, measure the 1-point function of the stress energy tensor in the presence of the defect. So these are the three anomaly parameters. And now the question becomes, can we find some observables associated with this surface defect that is completely fixed by these anomaly parameters? So the first observable we're going to measure or try to study is the defect cosmic energy. Now think about, I'm staying in flat space and there is a flat surface defect. If just working on this setup, of course, there's no scale. You cannot get any sensible result, right? So the thing is we can do, the idea is we can do the wire transformation, transform everything to a cylinder. Okay? There's a large cylinder, and now the surface defect is stayed in here. It's basically the equator of this sphere, and there's a time direction, additional time direction. So we want to measure how the defect changed the cosmic energy, okay? So I will first show the result we derive, which is basically given by two terms. One is controlled by the B central charge, another is controlled by this D2. So how to get these two terms? So you might notice that the first term is essentially analog of the 2D CFT central charge. Indeed, this first term just comes from the anomalous wire transformation of this surface defect. Okay? Because surface defect also has anomaly. The second term is D2, because D2 measures the one-point function of the bulk stress tensor in the presence of defect. So the second term is essentially you counting the energy supported by the defect, counting the energy flux in the bulk. Yeah, so this is the way to derive this one. So one can check this formula by explicit examples, for example, free fields, and also holography. In holography, you can consider there's a three-dimensional probable brane. You can also try to check this formula. Maybe the real interesting question is whether this can also be tested by the fuzzy sphere or even experimental. This I refer to in Chen and Slava's talk. Another question is how the defect changes the entanglement. So what is the setup? The setup is, if this is my system, this is my time direction, this is the time slice, and this is my defect, I want to consider a problem to measure the subregion entanglement. The subregion is bounded by this blue sphere, okay? Now, with the insertion of this defect, I want to ask how the defect changes the entanglement. That will be the question. So as you can see, it's a little hard to calculate in this original space, but fortunately, due to conformal symmetry, now the defect is also conformal, the bulk is conformal, so we can do the conformal transformation, send this system to some easier system. So indeed, if you do this wire transformation, the system will be sent to a circle times the hyperbolic space. Now you're asking me, where is my defect? Now the defect is wrapped on this tau circle plus this radial direction in the hyperbolic space. So 1 plus 1, there are two-dimensional orange objects. So there are many other papers that actually discussed the similar question, see how defect contribute to entanglement in these papers. Yeah. For example, we can take examples, let's say, we can take the free field, the surface defect examples in 6 dimensions. You can easily write down these conformal surface defect examples. One can compute these free field examples in this right-hand side system. So we can compute the thermal partition function, basically, and one can compute the Rayleigh entropy from here. Yeah, so there is a important thing is one should not forget, in this case, forget this boundary term. Because in the original space, if you want to do replica trick to calculate this entanglement, there will be a conic singularity. Now you want to resolve the conic singularity. This will bring some boundary terms because there is a curvature coupling. Taking into account everything, one can try to, this is the result basically for the free scalar. One can check against this known formula. Actually, the surface defect contribution to entanglement entropy formula was already derived by these people some years ago. So one can plug into this data, check against this formula. The point is now in this framework, we can compute the defect Rayleigh entropy also. Now we start to ask the further question. So, because in 2D CFT, we have a compact formula even for Rayleigh entropy. Now you might want to ask, for the surface defect Rayleigh entropy, is there any or similar universal formula as some function of n or 1 over n? Is it possible to find some closed formula? That's the question. So in general, for general CFT or surface defect, it's hard to answer this question. But if you consider some supersymmetric one, then we found that indeed there are some closed formulas. So then let's move to this supersymmetric case. So let's consider this first supersymmetrize this Rayleigh entropy. So the thing one can do is one can twist this theory by the R symmetry on this background. This gives us the so-called supersymmetric Rayleigh entropy. It was first proposed by Nishioka and Yakov in 2013. Then we generalized this to the higher dimensions. Now, some years ago, this twisted Rayleigh entropy in the 6th dimension 2-0 theory was also derived. So this is the universal coefficient in front of the log term. So as you can see, this is completely fixed by the conformal anomalies. This A bar and C bar are the wire anomalies for this theory. There are known formulas for this A bar and C bar. And this R1 and R2 are just the twisting parameters. They are not important, okay? Just because in this theory, the R symmetry is SO5. There are 2 catons. You can take use of these 2 catons to twist. So you have a free choice. The R1, R2 are the background parameters. One can check this formula, using free theory and also holography. You find a precise consistent with the explicit examples. And now this is the bulk. It's not yet include the defect. So with the defect, what can we do? Turn to this ADS-CFT. If we want to, ADS-CFT can also, in ADS-CFT, there's also a precise holographic dual or supergravity solution due to this twisted Rayleigh entropy. It's something called the hyperbolic black holes. Okay, it's a hyperbolic black hole with 2 charges. Okay. Now, in the ADS-CFT, you can do some very easy calculations to find this defect contribution to the twisted Rayleigh entropy. Because we know for half of BPS surface defects, the holographic dual will be M2 branes. Now you can put an M2 brane in this ADS space, try to find this M2 brane contribution to the twisted Rayleigh entropy. Okay? Then you get some result. The result looks very simple. The result just the defect contribution to the twisted Rayleigh entropy is just a linear function of 1 over n, as you can see, with some coefficient. This coefficient essentially turned to the CFT parameter is essentially linear to n. Okay. So this is still very limited data, but we want to first conjecture or claim close the formula for the defect contribution to the twisted Rayleigh entropy. We want to claim there's a closed formula for this half BPS surface defect in the 2-0 theory. It's controlled entirely by this linear combination of 2 anomaly parameters. As you can see, the other structure is just similar to the 2D CFT result. These are the background twist parameters. This is, again, as you can see, this part is linear to 1 over n. Okay, this is linear to 1 over n. There is a logarithmic. Now you ask me how to derive this result, and this result can be derived from the defect twisted cosmic energy or defect supersymmetry cosmic energy. Previously, we showed a formula for defect cosmic energy, which is not supersymmetric. Now, there is also a supersymmetric version of the defect cosmic energy. The point is this Rayleigh entropy formula can be derived from the cosmic energy formula. Okay, there are some details, but we don't have time to explain. But just trust me, because we try a lot of effort to try to justify these 2 formulas, and we believe they are correct because they passed a lot of tests. So what is the defect supersymmetry cosmic energy formula is this one, given by two parts. One is controlled by D2 minus B, the other is 2B minus D2, okay? This omega 1, 2, 3, and sigma 1, sigma 2 are the chemical potentials for the rotational symmetry and the R symmetry, okay? Essentially, they are the background parameters. So how to justify this formula? So defect supersymmetry cosmic energy formula can be computed from the localization. So how? Because 60-20 series do not have Lagrangian action. So how do we do the localization? The idea is that we can try to do the 5-dimensional maximum super Yang-Mills localization to calculate this cosmic energy. And so we found that the localization results are consistent with this formula, and also this formula can be confirmed by the equivalent integral of the Orlomony polynomial. Okay. So we believe this is correct. So in the remaining time, how many minutes? Okay. So in the remaining time, let me try to explain some details how to get there, how to justify the formula. So first of all, this is the due to a connection between 6D theory and 5D theory, I can try to do the localization calculation. As you can see, for the bulk, one can derive this cosmic energy. Now we want to ask further how the defect contributes to this cosmic energy. So what we should do is insert this defect, include this defect insertion in this localization formula. So in 5D, this becomes some Wilson loop, okay, along this S file. So you do this, you write down this matrix integral using the set point techniques, try to work out this result. So for symmetry representation, you get this result. For anti-symmetry representation of this result, because here we are working on the A type of 2-0 series. So you find that these two results, perfectly consistent with the conjectured formula. Now, that formula is also consistent with, can be reproduced from this equivalent integral of the Orlomony polynomial. So, because this is a 4,4 surface defect in 2-0, this is the Orlomony polynomial result. If you do the equivalent integration, it's essentially, after this integration, essentially these C2s replaced by the chemical potentials. Now you carefully identify the 2-dimensional and the 6-dimensional parameters. Then you find that this result can be written in a compact form due to this recently found B and D2 formulas for this type of surface defect. I think given in this paper, then you can come up with the compact formula. Looks like this. Now, starting from here, you can also justify the Rayleigh entropy formula, and they are perfectly consistent. Okay, let me conclude. So we derived the universal formula of the surface defect cosmic energy in terms of wire anomalies in D-dimensional bulk. The next question will be, is there any numerical experimental verification? We also obtained a closed formula for surface defect to contribution to supersymmetric Rayleigh entropy as well as supersymmetric cosmic energy in terms of anomalies in this 60-20 series. The next question will be, can this method be used for some other types of defect, also in other dimensions? Okay, I will stop here. Thank you.
Okay, question session. Yes?
Yes, thank you for the interesting talk. So by anomaly polynomial, I think you mean the anomaly polynomial for the 2th anomaly for this, these SU2 symmetries, right? Not for the well anomaly.
Yes.
And the role of well anomaly is that the coefficients is involved in the coefficients of those term classes.
Yeah, but these anomalies are related due to supersymmetry.
I see. So is the algebraic form of the well anomaly play any role in this discussion?
Sorry, I didn't hear last.
Is the algebraic form of the well anomaly play any role in this discussion?
Algebraic form of well anomaly.
As a curvature polynomial.
Yeah, I think so.
Or I should ask, so it seems like there's an interplay between the well anomaly and this toothed anomaly. Does it imply anything fundamental between the two anomalies? Maybe at the cohomological level, for example. And seems like this is enforced by the supersymmetry in this specific case.
Yeah, in my understanding, it's just due to supersymmetry, it's just related.
Okay, thank you.
What is the interpretation, physics interpretation of Wilson loop in this case?
What is the interpretation of
Wilson loop in
Wilson
this
loop.
case?
Wilson loop.
Yeah.
Okay, good. Okay, good. So interpretation of Wilson loop. You mean the Wilson loop in this localization or?
Yeah, Wilson loop. Yeah.
Oh, okay, good. So the point is the surface defect in 6D after reduction to 5 dimension, because the surface defect wrapped the additional circle, so it becomes a loop operator.
Okay.
Any other questions? We do have time for more questions.
Thank you for the great talk. I guess I have a basic question. Is there any interest in Worshi theory with defect on it?
Good. Now here, by the defect, we define the defect in quantum field theory, which means it's the infinite tension object. Yeah, it's not a finite tension. It's not a dynamic object. So
I see. So somehow it's in tension with.
Yes.
It's not ghost string theory.
Yes. Yeah.
I see.
If you insist to integrate out the block, you might get some non-local series.
I see.
Yeah.
Interesting.
It's not dynamic. There's a question over there.
So since these different combinations of the B and D2 anomalies shows up in your Renyi entropy,
Yes.
do you think there's a way to argue, for example, D2, which appear from a linear combination, has some positivity property? I mean, it's believed to be, this is stress tensor one-point function, right?
Yes.
It's believed to be positive, and there are conjectures on that. Do you see a way of proving that using the quantities you have constructed and some inequalities that may be argued there?
Yeah, that's a good question. We thought about this for a
example,
moment.
for the Casimir energy, where different combinations show up, you can construct D2 from a linear combination.
Yeah, for example, okay. Yeah, you might want to argue this coefficient is positive. Yeah.
No, that is not positive because B can be negative. So my question is because D2 and B show up as different linear combinations, for example, in the Casimir energy, if there's an argument of, for example, the angular contribution versus the R-symmetry contribution, relative magnitude, you can use that to argue the positivity of D2.
Okay, let me first finish. So for this positivity, I mean, because this formula is only true for a supersymmetry case. You cannot just separately say it's not positive. There is a possibility it's positive.
It's not positive even in supersymmetric case in general.
Because this is for the 4,4. For the all the known examples, let's say different representation of the surface defect, we check that these are all positive.
In the example you check, but not in the general case.
Okay.
Yeah. For example, if you consider boundary conditions of ABGM theory,
okay,
you can have B being negative, just coming from the fact that the ratio boundary condition remove degrees freedom, give you a negative B. But yes, for surface defect in 2,0, it's going to be different. Yeah.
Okay. Any more comments? Yes. Here.
Thanks for a nice talk. I just have a question. Maybe it's not directly related to what you are doing, but maybe there's a relation. So if you take this conformal theory and deform it away from the conformal point,
yes,
by separating the M5 branes and then stretch M2 branes, you get a string between them.
Yes,
yes. People have computed the elliptic genus of the twisted elliptic genus of that and so forth. You get these partition functions. Are there any connections between for example, your supersymmetric Casimir energy and those partition functions? And is there any connection that you have studied or anybody studied?
Yeah, I think they're related. I think what I'm referring to is some kind of index, right?
Yeah, what they call the M, what's called the M string.
Yeah, yes. Yeah, it hasn't been clarified, but I think it's related. Yeah.
Okay.
There's a comment.
Sorry, just a comment on Cormoran's question. So indeed, the exact formula for the Toff anomaly was calculated by going onto the tensor branch and matching with the answer from M string.
Yeah. Okay, any other questions? If not, let's thank the speaker again. So let's have a coffee break.
Can you hear me? Yes, it works. Yes? Okay, good.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
マイクです。
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Should I wait for Yao or no? All right, are you ready? I hope you guys enjoy this strings conference. There's a famous idiom in Chinese called 天下没有不散的宴席. But let's enjoy the final two talks. Here we go. Hua Xinju from Peking University, from correlation function to charge correlators in QCD. Please.
First, I would like to join the other speakers to thank the organizer for inviting me to this conference. Actually, this is my second time to string conference. The last time I came here was 20 years ago in 2006 when I was an undergrad student. I remember vividly, it's at the Beijing Friendship Hotel. Unfortunately, I wasn't able to do anything useful to string theory, so I feel a lot of pressure to actually presenting a talk here. So my hope was that I could give at least an entertaining talk that tried to bring string theory to experiment. But after listening to Slava's talk, I gave up that idea because no one can be more practical than selling a conformal coffee machine. But anyway, I still need to deliver my talk, so that's it. I'm going to talk about from correlation functions to charge correlators in QCD. And this is a series of work that collaborate with Hao Chen, a postdoc at MIT, Pierre Moni, and Gerardo Vita, staff scientist at Sun, Zhao Yanpang, a student in Beijing, and Zheng Xu, a postdoc at Daisy. Okay, let me start first from something maybe some of you may have heard of, which is energy correlator or energy detector. So let me use that to set up the stage of my talk. So my talk would be more practical about how to measure things. And you know there are many ways you can measure things. On the left is the most famous CMB, which is unique in the sense that there's only one event for this important thing. And from my understanding, because it's so rare, you want to try to understand everything, try to understand the best what you are measuring. So you want to decompose into 2-point, 3-point correlator, for example. On the right, there's another type of measurement that's very important, which is the event that discovering the Higgs boson. And here, the key thing is that we want to look for anomaly. We have many events, and burying those events, there are some rare events that actually produce the Higgs boson. So you try to use all information you can have, which includes any number of correlation functions, the full shape of these anomalous events. The detector correlation or energy correlator is kind of mix of the two, in which sense we have many events in collider physics, in particular for events that related to QCD. And we want to try to understand these events in the simplest possible way. So we want to decompose them into 2-point correlation, 3-point correlation, for example. So the way that these are measured is the following. We look at these particles that produce in the collider, and we measure their pairwise correlations. And for each pair, we have some weight. The weight is, for example, related to the energy of the pair of particles. You can actually overlay all these events because now it's a statistical correlation function. So the plot below is actually by overlaying millions of events, you can get a plot very similar to CMB. And the whole idea that actually go back to 50 years ago, and in the early times, important question in QCD is how to design an observable that can be computed reliably from first principle. And this is under the name of infrared safety. If you have an observable that doesn't have any infrared divergence, maybe you can directly compare that to your experiment. And there are two lines of thought during that time. The first one is in 1975, George Sterman proposed that if you look at the energy of some particle flowing in some direction n, for example, and you weight that event by its energy, this will be an infrared safe measurement. because the energy is additive and also is insensitive to soft particles. And that idea in a few years later has been brings to an actual meaningful observable in E plus E minus collider, which you can measure correlation function between different angles, weighted by the energy of the particles that go into those angles. Around the same time, there's another very important paper by Sterman and Weinberg, which is, for the first time, people defined a concept of jet that mimic the underlying quarks or gluon that produce in these events. This idea has taken off since then. So basically, every experiment is trying to measure something related to jets. But the original idea of correlation function is not much attention was paying to this part. The things change only from the experimental part. The things only change in the past few years. And I think one of the reasons that change things is really there's more. You can play more theoretical games with this kind of observer related to the correlator of these energy operators. So here is the definition of the energy operators. They're also called ANAC operators, and I think many of you are very familiar with that. Here we are going to measure this operator in the boundary of our space-time. So you need to take the detector limit, which will put the operator or the stress tensor to the boundary, and then you do a detector time integral. In a conformal field theory, that's just from the bulk to the boundary is just a conformal transformation. But in QCD, something is different. Because we know that when you go to the boundary, you are entering this gap phase of QCD. You're not going to see any interesting dynamics. So QCD is essentially a free theory in the actual boundary. So this detector actually is trivial there. It can be written as creation and annihilation or number operator weighted by energy, let's say. So it's a trivial operators. But still, you don't know how to calculate. If you want to measure, if you want to calculate correlation function of these guys, you don't know how to do that. You need to, because the only fundamental theory that we can use is QCD, which is written in the degrees of freedom of quarks and gluons. So to actually calculate correlation function for these detectors, you need to match to something you can calculate perturbatively, which is a detector before hadronization or before quarks transits to hadrons. So there you need to, there is an assumption that you need to make in order to calculate something. The assumption is that these hadronic detectors can be matched onto a series of partonic detectors. So these partonic detectors, they are written as asymptotic free quarks and gluons, the number of operators of these asymptotic free quarks and gluons, and weighted by some energy. And this matching will be unusual because you are matching from IR to UV. And there will be non-perturbed information sitting in this Wilson coefficient that we don't know how to calculate directly, but we can try to measure from experiment. What we can calculate is the correlation of these partonic detectors because it's written in terms of quarks and gluon at high energy scale. So that's the main ideas of how we calculate observable related to energy correlator. And there are actually not just one detector you can construct, not just weighted by energy. There's actually many things you can do. So the energy detector is actually the stress tensor. If I draw a true Fairchild plot, the energy detector, energy operator is sitting here. And the transformation or the light transform actually swap the local scaling dimension and spin to the detector spin and detector scaling dimension. So there's a swap of a quantum number. But anyway, the key point is that as an experimentalist, they can control the Lorentz spin of your detector. Basically, this Lorentz spin will relate it to the exponent of how much energy the exponent, the energy weighting you want to put into it. So experimentalist has the ability to move a vertical line around this true Fairchild plot. And if you want to measure energy, then you put a line here, and this line will cross several Regge trajectories. And each of those Regge trajectories will contribute to your observables. And this is known, this 45 degrees line is known as the Diaghilev trajectory, which is very important in QCD, and it has been computed since 1970s, and we only get it to 4 loops only recently. And there are also this BFKL trajectory, famously related to high energy scattering, but here you can also measure it or see its effects in this energy detector. And actually, there's even nicer things. These are not just a single operator there, as we all know, they are actually form an analytic family. So they actually continue to a whole Riemann surface, but not in QCD. In QCD, this is poorly known, but in Engels-4 Silver-Yang-Mills theory, this plot, you can plot it in the plot the full Riemann surface for it. And a detector is putting a line, a vertical line here. An experimentalist would put a vertical line, depends on which Lorentz spin they want to measure. And that vertical line will hit multiple partonic detectors. And the calculation will use information of those points to make a prediction for experiment. That's the main setup. Okay, so then you can go ahead and do calculation or do measurement for different point, 2 point, 3 point, etc. And you can do measurement for different state per psi. The simplest state would be a E plus E minus collision to a photon or a Z boson. That's created by electromagnetic current and a Fourier transform to a momentum eigenstate. And then there are two useful ways to calculate if this observable. The first one, as it was defined, you can, it is defined from some local correlation function. So you can try to light transform a local correlation function and then get what you need. But that's kind of difficult because this correlation function are Weitermann function and in Lorentzian space-time. But there are techniques people have developed that significantly simplify this procedure. The other way is to insert a complete state here, such that you can use the fact that the energy detector acting on these states will produce the energy of that particle. So you turn this calculation into a weighted cross-section. In both ways, you should get the same results. But that's only tested in Engels-4 Silver-Yang-Mills theory. So part of the motivation for this talk is actually try to look at it in QCD and see whether they agree with each other. And there are many, the interesting part is that there are many experimental efforts going on in this type of observable. This is one of it. People actually use the old data from the lab error to reanalysis the lab data to get the hitherto most precise measurement of energy correlators. And the interesting story is that this data, the data is measured back in the 1980s, and they are locked in a computer, but unfortunately the computer has a password and no one remembers the password of that computer. But LLM comes in to help. So AI comes in to help. Nowadays with AI, anyone can hack in an old 1980s computer. So they can dig out the data and make an actual plot of it. There are many interesting physics going inside this plot, but I would like to point out two that's not totally clear. The first is that in this region, you see clearly the signal of seeing something related to light rate operators. So, but light rate operator is only, as a operator, is only understand better in a conformal field theory. So one need to have whether we can have a better non-perturbative definition for light rate operator in QCD that would be relevant for experiment. The other interesting limit, this is the back-to-back limit, where the detector at large angle. People believe that there's something related to string breaking here. So one would ask whether you can develop a theory that actually describes this region using a string, for example. But so these are more, there are more experiments ongoing. So what I want to show here is that right now there's a lot of experiment going to measure this correlation function. If you have any interesting thing you can test for correlation function, maybe this is a good time to go to the experiment and ask them, and they would be extremely happy to do it for you. Okay, now comes to the charge detector. So the reason that I'm going to talk about charge detector is that this is the only other protected current in QCD. So it's sitting at spin equals 1 and delta equals 3. So because it's a conserved current, so you don't need to worry about its renormalization. And the question is whether one can construct interesting and infrared finite observable out of infrared calculable observable out of it to probe interesting physics. And that has been actually, there is some interesting physics you can try. For example, hadronization. If you think about hadronization, you have the quarks carry fractional charge, and then you have hadron carry integer charge. So the charge must be, there's something interesting going on for the charge redistribution during hadronization. And that's, people have proposed to measure positive charge and negative charge correlator. It would behave differently from say charge energy correlator. So there's, of course, there are experimental motivation. And even back in 1979 or 1978, T.D. Lee gave a series of lecture about particle physics in China. And already, and then he come up, he wrote a textbook on it, and on that textbook, they actually already, he talked about charge correlation. So you weight a pair of particle by its charge, the product of its charge. But he also point out that, unfortunately, this is not infrared safe. So you cannot calculate it beyond basically 2 loops. This is an important question, even nowadays, experimentally, because you can replace the charge by other global quantum numbers, such as flavor. So there's active study about it in the LHC. So now our goal is trying to understand better charge operator or charge correlator, see how we can make sense of it. So at 2 loops, as T.D. Lee pointed out, the only configuration that leads to infrared unsafe is this type of Feynman diagram. You have a soft gluon radiating a split into a QQ bar pair. The soft gluon gives you some infrared divergence, but it was not canceled against the virtual diagram, because the virtual diagram, the gluon doesn't carry electromagnetic charge, so there's no cancellation between the virtual and real. However, there's a one limit that this divergence is disappear, which is the limit that if your detector is in the back-to-back configuration, the matrix element itself is suppressed in that limit. So you can take advantage of that limit to get something at least is infrared finite at leading power. My first goal is trying to understand how that's happening from the correlation function perspective. As I told you, this observable, the charge-charge correlator, can be obtained from a local electromagnetic current correlation function and do some transformation. But this local JJJJ correlator is obviously finite. So how does infrared finite appear or disappear in this process? So that's the one thing that we try to understand. And if there's a lot of data, then it would be easy to see how it appear or disappear. But unfortunately, there's not many data you can use. Because this 4-point correlation, off-shell correlation function is very hard to calculate. In QCD, we currently only know about it at 1 loop's order. And unfortunately, at 1 loop, you cannot see any sign of infrared divergence or not. Because at 1 loop, this behaves exactly like a conformal correlator. There's no signature of running coupling or whatever. So you need to go to 2 loops. And no one can do the calculation for it at 2 loops at this moment. So we need to take certain limit to simplify. So the limit that is really what I talk about, which is the back-to-back limit. In the back-to-back limit, the configuration that is important for the 4-point function is this. So you have the source and sink sit at x1 and x3, and your detector at x2 and x4. And they are in a sequential Lie-Cohn limit. And in particular, x24 is much larger than x13. And this configuration is conformal equivalent to this configuration that people have been studied before, which is the sequential Lie-Cohn limit, but there's no hierarchy between x24 or x31. And people know that this configuration actually has a very simplified structure, which if you take a ratio, it can be written just as a Wilson loop, which sit at the corner, or whose vertex sit at the corner of these operators. So my question is, can we find a similar factorization formula for QCD? And the answer is yes, and actually people has developed the relevant technology for this task for past 20 years. So I will quickly go through the techniques here. So the idea is to use an effective field theory of QCD, which called soft collinear effective field theory. And this theory is constructed as follows. You go to your loop diagram, for example, and you look at what dynamical modes are relevant for the divergence or the logs in those diagrams. In this particular case, for a form factor integral, the important modes are the hard modes where all the momentum are at the scale of the hard scale, the high energy scale, or the collinear modes where the particles are flowing in this direction with the collinear momentum, or soft modes. So if you decompose in the Lycon coordinate, you can assign a counting parameter lambda to each mode. And there are two interesting effective field theory. You can construct it in this way. The first one is called SCT1, where the three type of modes, they all sit in a different scale hierarchy. Or the SCAT2, where the collinear mode and the soft mode are sitting in the same virtuality hyperbola. So we can choose a specific configuration for our 4-point correlator such that we are in the SCT1 region. So we choose this particular pseudo-Euclidean configuration where x13 and x24 is the largest. And this and yi, which is the distance connecting x1 and x2, etc., they are the second largest scale. And then the shortest distance is the position offset of each vertex. So this is a SCT1 configuration. Then you can apply the SCT technology to calculate this correlation function. The interesting thing is that you can, by doing that, and there's a whole machinery you can use, so this derivation is basically straightforward. But the interesting, I want to emphasize that then you can derive a factorization formula for the 4-point function, which has a different ingredient, and all those ingredients are well known in QCD. So you automatically get a prediction for this local correlation function in this particular limit to high order. Okay, now we have the correlation function in the sequential line limit. Line limit. We want to turn it to the detector limit, which is non-trivial because the factorization formula is not written for that limit. And you can actually see from the data, which has certain logs, which makes the detector limit not commute or not continuous. So we cannot do that. But here, again, we can make use of conformal symmetry. So this is a trick that we can use. You can go to a conformal fixed point, which is the, here we can use a Wilson feature fixed point. In this fixed point, the two limit is connected by conformal symmetry, and then you use conformal symmetry to bring your correlation function to what you like, and then you do some subtraction. Then you can get what you need. So the story is that we can get the QCD results from this local correlation function, but there's some trick. You need to use conformal symmetry to do that. Now come to the last part of my talk, which is that we want to go beyond this back-to-back limit. We want to understand how to, we know that there's an infrared divergence for generic angle, for example. And how do we make sense of these configurations? And the configuration, this divergence is non-local. It depends on the angle of the detectors. But in QCD, we know many non-local IR divergence before, for example, Parton distribution function. This is a famous example where you have non-local divergence. And we know that you can take a Melling transform to localize it. So here the question is, what kind of transformation we can use to diagonalize this divergence? And here a useful, so to do that, we first need to understand where the divergence is coming from. So here the line rate OPE, which is the type of OVE relevant for this detector operator, is useful here. And this charge detector, they have quantum number, scaling dimension 0, Lorentz spin -2. So by counting the quantum number on both sides, you would find that all the operators on the right-hand side will sit on this line, exactly on the BFKL trajectory. And that is the reason why this observable is infrared divergent, because they are sitting on this line. And this line is coincident with the other bound that people have studied about, which is the commutativity of short wave, which I don't have time to go into. But it also makes things very complicated. Now you want to calculate, you want to understand the right-hand side, you need to understand all of these operators sitting there. But they are very complicated because these are the point where the BFKL trajectory is mixing with the DGLAP trajectory. So you need to demix those trajectories. There is yet a simpler way that also comes from string theory and conformal field theory to make this task simpler, which instead of looking at all those local operators, you can try to look at the principal series. So we can do a harmonic analysis on this charge-charge correlation function. The kernel is determined by symmetry. By this harmonic analysis, you get a observable which is living on this principal series line, basically. So experimentalists now can measure the charge-charge correlator with this quantum number. And the observable now, what they measure depends on this JL on this trajectory, and it has two parts. The first part is the perturbative part, whose divergence we know how to subtract at least to 2 loops. There are a second part which is related to the BFKL trajectory on this line, whose operator definition in the perturbation theory we also know how to write down. So the actual thing is that now we know how to compute the perturbative part and how to parameterize the non-perturbative part. So here is a comparison with simulation data. The perturbative part, we have a very powerful tool called Pythia. The perturbative part is called the parton level here. The fully non-perturbative part is called the hadron level here. You can subtract the 2, and then you would get the contribution from this new fully non-perturbative part. We want to test whether our understanding of this part is correct. And we can fit that contribution at some certain energy, let's say Q equals 200 GeV, and then runs it to different energy using the information we know about, which is the eigenvalue of the BFKL trajectory. And it agrees pretty well for small imaginary JL. And when it goes large, there's some numerical problem, make things not agree that well. But actually, this seems to provide a way to directly measure the Regge intercept when at this point it corresponds directly to the perturbative Regge intercept, and the results show you that this is an intercept that's bigger than 1. That brings to the end of my talk, and also I think I run out of time, so I will just stop here.
Question.
Thanks for a great talk. Can you explain what is the reason that people are now so interested in this energy correlators? Is it a practical reason? Is it a conceptual reason? Why are these observables better than the ones that people used up to now?
So I don't want to say this is better than that. That's certainly not the reason. But just because you have something new to measure, I think that's an important reason. That's the first important reason. And the second important reason, it does help you to see something that's difficult to see previously. For example, this region is this region is an angle. This axis is an angle axis, and you can turn it to the energy scale. If you look at the energy scale is roughly at 1 GeV, 2 GeV or not. If you use the traditional way, let's say measure a jet mass or something like that, it's very hard to have a good resolution in that region. So it gives you a way to probe. For example, this region, we believe, is describing how quarks is transist to hadrons, which is hard to observe previously. So that's the first reason. And the second reason that related to more theoretical point of view, which is that These are much simpler observable than what experimentally typically try to measure, and which means that you can have better analytic control of many of these measurements. And the fact that it related to correlation function, 4-point correlation in this, that also, I mean, the developer conformal bootstrap helps a lot in advertising these things. Yeah.
Okay, in view of time, one more question.
Hello. I'm not sure if this charge-charge correlator also related to the hadron spectral function.
Hadron spectral function.
Yes.
So, no. So the charge is not directly related to their mass or their energy. So the charge, the particle, so here the charge detector doesn't care about the energy of the particle. It can be very soft or can be very energetic. As long as leave a track on the detector, you can see it, and then it gets into your distribution. So in other sense, it's not measuring it would not tell us. I think would not tell us much about spectrum, but will tell us. But I think it's going to tell us a lot about perturbative BFKL physics, or maybe subleading BFKL physics. Yeah. That's something related to high energy scattering, but now in a very different kinematical setup.
Okay, thank you.
Okay, let's thank the speaker again. All right, the final talk is given by Yifan Wang from New York University. He's going to tell us about the topologically lost.
All right, thanks for the invitation, and thanks everyone for staying till the last technical talk. And I personally have enjoyed a lot this conference. I've learned a lot from talks and from talking to many of you. And today I will share with you some thoughts on in the world of defects and symmetries. And together we'll go through a journey, a dynamical journey, and hopefully it will be fun. And one disclaimer is that if you see something cryptic on the slides, those are Chinese idioms for those of you who understand Chinese. Hopefully you will enjoy them. Some of them with my own twist. For those of you who do not read Chinese, want to understand them, you can ask me afterwards. Okay. Without further ado, let's start. So as is the case probably for many of you, we want to understand many-body phenomena, and one very powerful tool is coming from quantum field theory. And in this quest to understand many-body phenomena, especially the strongly coupled type, which is of particular interest, one guiding question is to understand the possible phase structures and the transitions. And in this quest, there are two important lessons that we have learned. One is the power of symmetries, which we take as very secret. It's very powerful. It's universally applicable. And the other that has been appreciated more and more recently is the virtue of defects. What do I mean? In particular, the notion of symmetry has been generalized recently enormously. In particular, this definition of generalized symmetry is now in terms of topological defects. And furthermore, the interesting representations and symmetry twist for the corresponding symmetries are going to be described in terms of yet another different kind of defects in general, and they are mostly non-topological. And together, these charge operators, symmetry operators, and their charged objects, they together encode intricate symmetry structures and anomalies that show up in various quantum field theory models and lattice models. But there is actually more to defects than just encoding symmetry structures. So I want to emphasize, first of all, that defects are really ubiquitous, and it's something that's already mentioned by Yang's talk. And it has various distinctive features. And this is a subject that is not new. It's a really old subject. It has been studied by many people previously. I want to highlight a few works. For example, the one from Kondo that studied spin impurities in electron gas almost 60 years ago. And then the work from Kay and Fisher that studied charge impurities in the Tomonaga-Leffinger liquid 30 years ago. And in recent years, there has been explosive amount of recent work that study various incarnations of defects and their physical consequences. And the reason that people are interested in studying defects is because these defects provide a factory of interesting theoretical problems. They show up as impurities, Wilson lines, and D-branes described by boundaries of two-dimensional CFT. And this study of these problems are really catalyzed many develops in quantum field theory. Just to give you some prominent example involving Wilsonian formulation of RG, the integrability, conformal field theory, supersymmetry, and many others. And also in the string theory context, a study of defects, in particular boundary conditions of two-dimensional CFT, has motivated many developments in open string field theory and complicated and very interesting questions of tachyon condensation, which was reviewed in Ashok's talk. And a general lesson that we have learned from many of these explorations is that defects are really a universal, it's really a unifying principle, a perspective, describing various strongly coupled phenomena in quantum field theory. And one important example to keep in mind is the detect as an other parameter for example, confinement phase transitions in gauge theory in the case of Wilson loops. And as I already mentioned in the previous slide, just as a way to encode structure in the bulk CFT, defect is pretty efficient, and many quantum field theory questions thus can be reformulated in terms of defects, can be precise in this way, and allow us to diagnose its detailed structure. For example, entanglement structure of states in the quantum field theory can be formulated in terms of correlation functions involving Renyi defects. And lastly, apart from encoding structure in the bulk, defects also has interesting phenomena that's intrinsic to the defect world volume itself. For example, novel universality classes that are not present if you consider isolated local quantum field theory. And I want to emphasize that these interesting questions can be answered by understanding the dynamics of defects, in particular the RG flow associated with couplings that are introduced when you include defect in your system. And this should be thought of as an important step towards the ambitious goal of trying to complete QFT, where a lot of progress have been made in the context where the QFT is topological, but I should say a similar program to the case of QFT is at its infancy. So how do we approach such an ambitious program to constrain defect dynamics? There are several strategies. And one is to understand structural ingredients. This comes from the bootstrap philosophy, which is very successful applied to the context of CFT, especially the local operator algebra. So in this context, we want to understand, for example, a generalized notion of operator product expansion for defects. And the baby example is to understand this fusion product. Namely, you have two defects which are next to one another. And if you consider the limit where the transfer separation goes to 0 relative to longitudinal extent, can you reproduce the effect of their insertions by single defects? Some effective notion of fusion. Another natural question is to understand generalizations of the usual symmetry structure in the homogeneous quantum matter, but now refined by the presence of defects, and whether there are generalized notions of anomalies which are existent depending on the defect insertion itself. And finally, in the study of quantum field theory, especially dynamical questions, such as RG flows, it's very important to come with monotonic functions that give rise to non-trivial predictions of where the RG flow may lead us to. And for example, this RG monotone should also have extensions to the case of defects in the form of certain quantities which you can calculate in UVIR, and they must obey some rigorous inequality. So let me spend a few slides to contrast the difference between topological and non-topological defects, because both of them will play an important role in my talk. So topological defect is defined by this very important property. Namely, if you study correlation functions involving other local operator insertions, next to the topological defect represented by this solid red line over here, the correlation function will be independent of deformations of the topological defects as long as it does not cross the operator insertion. And furthermore, the operators in your theory will fall into representation of the corresponding symmetry generated by the topological defects. So if you really want to pass the topological defects across the operator insertion, you know what to do. You just have to change the operator to its transformed version. And this is a simplified example where the defect is invertible. Otherwise, I have to be more precise about topological junctions. And for those of you who have been familiar with this jargon, topologicality really subsumes the notion of conservation in the case of generalized symmetries. And in this context, the notion of a composition of symmetry transformation is formulated in terms of fusion. And then by forming various junctions of topological defects, you can generate a symmetry background, just like how you introduce background gauge fields in the case of invertible continuous symmetries. And a very important property in the context of topological defects is this notion of rigidity. More precisely, it's the rigid constraints on the structure encoded by topological defects, namely their fusion and their junctions. So in the sense that topological defects are really the purest form of defects that are subject to the most rigid law for defects. And this rigidity is behind its power, namely it gives rise to deformation invariance, as long as the deformation preserves the symmetry. And this can be used to lead to non-trivial dynamical predictions that tell you what kind of RG flow are possible given the symmetry properties. But the flip side of this rigidity is that there is no room for dynamics while remaining in the topological world. And thus, we want to consider the case where the defect is not topological as well. So what do I mean by defect non-topological? It means that these nice equalities that we talked about before, in the case when the red line represents a non-topological defect, no longer hold. Instead, it leads to very significant signature when you consider correlation functions in the presence of a non-topological defect. And here, I will give you an example of what's known as a conformal defect, where a local order parameter may develop a non-zero one-point function in the presence of a defect. In the case of conformal defect, the entire dynamical content is encoded by this coefficient, where the position dependence is fixed by conformal symmetry. So here, this is what I said, and we have already heard throughout the week about the different kinds of defects and interesting observables they lead to. And we have also just heard from Slava of how conformal defects can be a very efficient tool to actually directly test conformal invariance. And as was already mentioned before, currently the best universal approach to defect is the generalization of the conformal bootstrap program. But they come with various technical challenges. And complementarily, there are also numerical methods which are very efficient in specific settings, which we have heard from Yinchen's talk using fuzzy sphere. So the goal of my talk is to give you to generate some kind of analytic insights that may help us to understand defect dynamics. Okay? And for that question, a natural starting point is to start from deforming from our comfort zone, namely the defects which are topological. So here is the question that I want to address in this talk, namely what happens if you take a topological defect outside its comfort zone when the topologicality is broken. And I should say this is based on past works with my previous postdoc, Himanshu, current student Sasha, and previous postdoc Feder. And some of these things we're going to say is also discussed in my lecture at the GCS meeting in Paris in June. And I should also point out that I'm certainly not the first one who asked this question. I want to draw your attention to this, recent work, which study non-topological defects in a different way. And in a sense, the context I'm considering is slightly more general. OK, so what do I mean? So the question I want to ask is that start from a topological defect. Let's represent by curly L over here. I insert at a particular place in the space-time. And I consider deformations represented by operator insertion both in the bulk and operators on the defect. I suppose I proliferate all this deformation. And I ask, what happens to this defect in the infrared? Okay? If all the deformation I turn on commute with the symmetry, then I know in the infrared I get a topological defects. But here, I'm interested in the cases when the deformations, the operator insertions, actually do not commute with the symmetry defect L. So the kind of specific question I want to address is that what kind of structures, the rigid structures that we like so much about topological defects may remain? And the second question I want to understand is how do these remaining structures actually can constrain the defect dynamics? Okay? And again, as I emphasized, I will consider both bulk and defect deformations. And these mirror questions in the context of open-closed string field theory, if you consider the problem in 2 dimensions.
Okay. To make things very concrete, I will consider a particular starting place in the topological world, which describe the so-called Ising non-invertible symmetry, which have played an important role in many recent developments in the world of generalized symmetries. This is perhaps the simplest non-invertible symmetry. It's described by topological defects, which are denoted by eta, that generate the Z2 symmetry. This one denotes the trivial defect. And this curly n is the hero of the day that represents the Kramers-Wanier duality defect, which has this fusion rule that fuses this n defect, this Kramers-Wanier defect, fuses into the projector for the Z2 symmetry. And the fusion is not the only structure that's important to this symmetry. Other structure involving the F symbols that tells you how the crossing of other symmetry defects can pick up non-trivial faces in a non-trivial defect network. And here, example where you have the duality defect extending in this direction, and the exchange between a Z2 symmetry acting from the left and right pick up an interesting minus sign. Okay, I want to draw your attention to the sign. This symmetry was a symmetry of the Ising CFT, actually described completely the symmetry of Ising CFT, has been studied by many people. And it has also been realized in many other 1+1 dimensional CFT, including the monster CFT, and also on the lattice. And even more recently, this symmetry has been generalized to higher dimension to realize non-invertible symmetry, for example, in QED, in the massless limit. All right. So with this very concrete topological object in mind, let's gather some general knowledge that we have already about defect constraint on defect dynamics, which we will make use of in the subsequent part of the talk. So first notion is the defect anomaly. And here, to have the case where I have a non-trivial defect anomaly, we'll consider the case where the deformation does not break all the symmetry structure. It preserves the Z2 symmetry generated by eta. But I want to emphasize this Z2 symmetry by itself is really featureless. The Z2 symmetry doesn't have a Toff anomaly. So if you forget about other defects in the game, there is really no dynamical constraint from the symmetry alone. But there is an interesting structure when you consider the defect, even though the symmetry may consider the Kramers-Wanier defect as well, even though the deformation in turn may break the Kramers-Wanier duality. And this is coming from this picture that I already mentioned before. This minus sign can be thought of as the non-commutativity from the left and right D2 action. Naively, there are D2 that commute to one another, but this minus sign says that there's a projective representation of the symmetry when you have the defect inserted. And this anomaly was first discussed in this paper, and you can realize the anomaly concretely as a usual anomaly for one-dimensional quantum mechanical system upon folding this picture. And think about this anomaly as encoding the projective representation on the boundary that comes from folding this line defect. And this anomaly persists, as is the case with any anomaly, persists under symmetric deformations. And here, the deformations are required to be commuting with both the left and right D2 action. And as is the case with any anomaly, this predicts the infrared behavior of the defect under both bulk and defect deformation, as long as they have this symmetric property, must be non-trivial. In particular, cannot be decoupled quantum mechanics. And another important structural ingredient I want to introduce is this defect fusion, which I already mentioned at the beginning. It's a generalization of topological fusion to non-topological defects. Here is a subtlety in the non-topological world due to the Casimir energy, which leads to divergence in fusion. And you have to do it carefully, but this has been done in these papers, that one can extract the Casimir energy divergence and define a regularized fusion product, which is operator identity, which holds when you include the insertions transfers to the defects. And this has been generalized to higher dimensions, and there's a industry about understanding what is encoded in the fusion product of defects in higher dimension, which I don't have time to talk about in this lecture. Another important thing I want to mention is the notion of defect RG monotonicity, which is generalization of monotonicity theorem for QFT defects in CFT, and leads to universal inequalities involving various conformal anomalies, free energies, and entropy under defect local deformation, depending on which dimension you talk about. In the two-dimension, which will be in two-dimensional case, this is the Affleck-Ludwig G theorem, which says that the defect free energy when the defect wraps the circle, or the defect binding function, has to be monotonically decreased on the IR, under the RG flow. Namely, the UV value has to be bigger than the IR value. And the important fact to keep in mind is that in the unitary context, this G function coincides with the quantum dimension for topological defect. And in such a case, the topological defect G function is always bounded from below by 1. And it's invertible if and only if it's equal to 1. And there's an even stronger notion of monotonicity under RG flow for defects. This is known as the defect IR factorization discussed in the paper with Feder. So this comes from the, in the 2D context, comes from the realization that even the identity defect is actually unstable when the box CFT admit operators that has dimensions smaller than 1. But the more than unstable is something drastic that happens if you turn on this deformation, because you can use the G theorem to predict the UV value, because the UV value has to be equal to 1. For the trivial defect, IR value has to be stricter smaller than 1. As I said in the previous slide, for any topological defect, the G function has to be stricter, should be bigger or equal to 1. This immediately tells you the IR cannot be a topological defect. And in fact, the IR in the infrared, something drastic happens. The defect actually factorizes the spacetime into halves. And to give rise to a description for the defect in the infrared in terms of factorized product in terms of Carty states, and in particular, the boundary this correlation function between the energy between the stress tensor on the two sides is identically equal to 0. And this is a phenomenon which is not limited to 2 dimension, also holds in general dimension for codimension 1 flows. And this is the factorization phenomenon that was established in the paper with Feder. And there's many things interesting about this about such defects, but for the purpose of the talk, this will be bad actors for the kind of question we'll ask today. And instead, we'll impose rules that block this factorization phenomenon from happening, as we'll introduce him shortly. OK, so the hero of today, as I said, is going to be Ising defect. And more than the topological defect, I will introduce a notion of Ising-like non-topological defect. It will retain some of the properties of the Ising topological defect, but some of the properties will be lost, as is always a price you have to pay when you go outside the topological length. So we'll retain, of course, the Z2 symmetry. Sorry, we'll retain the Z2 symmetry. So these fusion rules are preserved. And furthermore, I will also assume the strongly Z2 symmetric property, namely the deformation will preserve the left and right action of the Z2 symmetry in the presence of the defect, so that this interesting projectivity phase is preserved. And furthermore, I will impose this Ising-like fusion rule to define Ising-like non-topological defect just to rule out the factorization phenomena. The point is that this fusion rule forbids factorization from happening for the deformed N defect, because the right-hand side involves only topological defect, energy transmission is always unity. And the left-hand side, if factorized, energy transmission, of course, is 0. So it will be a contradiction to this inequality. All right, so it's always good to look at examples where things have been studied in detail. And here is an example that everybody knows, the Ising CFT. And in these very nice papers from Affleck and Oshikawa, and also from the Bacchus, some of the questions that were already presented before have been addressed, maybe not put in the language that I'm describing here. So in this context, there is exactly marginal strongly Z2 symmetric deformation that you can turn on the topological defects describing Ising category symmetry. And if you turn on this deformation, you generate this non-topological defect represented by curly D. I index is for the topological defects. Kappa is the deformation parameter, which is exactly marginal. And these defects are non-topological, and the fusion product I also discussed over here. And you can check using the formula in this paper that in the case when I is 3, so representing a duality defect, and kappa prime are the same, in which case you take the minus sign here in the fusion product. You can check the fusion product is preserved for the deformed duality defect, and also the defect anomaly is matched throughout the deformation. And let's now graduate to the next interesting example, which is in the SIG1 CFT. In this context, perhaps less well known, but it certainly has appeared in many contexts in recent years, is that there's also Ising category symmetry in the SIG1 CFT at the bosonization radius, R equal 2. And I explained the self-duality under gauging the Z2 translation by eta in this case. And this duality symmetry, if you formalize, can be interpreted in terms of a carrier parity associated with the Dirac fermion. And this defect in this SIG1 CFT also admits strongly eta symmetric deformations, exactly that marginal deformation I see in the Ising CFT. And interestingly, here there are also other Ising-like defects, which can be represented by this projector over here, Remember, the icing-like defect, the way I defined, have to satisfy the fusion associated with the D2 symmetry, this projective phase. But the fusion rule between this defect and itself is relaxed with a coefficient, which is general integer. And this projector does satisfy those properties. So I will call that also icing-like defect. In this case, you can consider a deformation given by one of the Majorana fermions packaged in the Dirac fermion over here. And this holomorphic deformation, as studied in this paper, using some trick, can be used to deduce that the infrared behavior is given by precisely the Kramers-Zweinig duality. And here I want to emphasize that the right-hand side, if you fuse with itself, produce the left-hand side. And this RG flow dynamically takes the square roots in the sense. And here you can also study the anomaly matching, as I described in the previous slide, introducing the structure. And here, interestingly, the anomaly is matched in UV using the technology which is familiar in string theory, namely how the symmetry is realized on the Chempentner indices. And in this case, further knowledge of the holomorphic deformation ensures that the topological this defect upon the deformation actually preserves translation symmetry, and you can use that to predict that in the infrared has to be a topological defect. And knowledge about topological defects of rank 3 pins down the only possibility to be the duality defect. And this way, without using the trick used in this paper, you can directly predict the flow just using the symmetry that's preserved by this deformation and the corresponding anomaly. Let's go into a more interesting example, namely we want to study in addition to defect deformation, but also bulk deformation. Here we can, to make this study of this defect more systematic, we fold this defect along the insertion and consider corresponding boundary condition for the SIG2 to CFT. And the bulk deformation we consider is the exactly marginal deformation of SIG1 CFT, the corresponding to change the radius. But the deformation, general bulk deformation, will induce subtle deformation on the boundary, and this is a question that was studied in this paper. It's very subtle, but here you have to trust me, this can be done. And you will find a family of conformal defect which transport the topological defect away from the boson derivation radius to the arbitrary radius. And they're described in terms of D0, D2 bound states with 2 units of world volume flux. And in this context, in an interesting way, the defect anomaly I mentioned before is matched by non-commutative translation on the world volume of the D2, which is a fuzzy torus. And then you can also check the fusion rule by unfold this boundary condition to a defect in the SIG1 CFT and using the results in the paper from Bacchus and Brunner. And you can confirm that it does obey the icing fusion rule. So it qualifies in calling this icing-like non-topological defects along the entire circular branch. And we can further transport we can connect the two kind of flows that we have considered so far, namely a boundary flow and the bulk flow between icing-like defects. And here in the vertical direction is the defect flow I talked about between icing-like defects. In the UV is this topological one. This decomposable in the IR is the interesting topological Kramers-Zweinig duality defect. If you transport in the horizontal direction, this duality defect becomes not topological. Of course, this eta symmetry is common to the entire circular branch, so it stays topological. And at some radius, these two defects exchange rule because this operator cross dimension 1, and then they invert into RG flow between this non-topological icing-like defect, which is decomposable, into this decomposable topological icing-like defect, which is simply the projector. And you can check that everything is consistent between the relevance of the operator and the G theorem concerning the G function for the defect, non-topological defect. And there's some interesting relation I don't have time to talk about, so I may skip that. And in the string theory picture, what this means is that in the ultraviolet, the defect is described by a pair of D1 branes that come in from folding. They're wrapping diagonal cycle on the T2, and it displays in the transfer direction by pi. And this deformation amounts to an open string tachyon that carry transverse winding, half winding, and longitudinal momentum to the D1 of 1 unit. And what happens is that this pair of D1 branes resolve, they get sewed together into a D2 brane with 2 units of D0 flux. And I recently found out after talking to Ashok, this is a generalization of the descent relation between branes in S1 that was studied by Ashok almost 30 years ago. And the generalization here amounts to considering tachyon condensation with interesting combination of both winding and momentum charges. There are generalizations of this story to the case with ZK Tamaramagami symmetry, which is present as a topological defect at special radius. And one can again play the same game of transporting this defect on the entire circular branch, and that can be done. And furthermore, you can also understand a flow between you can understand the symmetry structure, namely the left and right ZK symmetry action, and how the corresponding anomaly associated with the back character of the Tamaramagami category is matched on the, in terms of the corresponding brane coming from folding the non-topological conformal defect. And in particular, the fuzzy geometry on the D2 brane, which is represented by this projective face, matches the anomaly coming from the topological defect at this special radius. And again, you have this interesting square root flow coming from this combination of topological defects into the infrared non-topological defect at general radius R, generalizing the result for k equal to 2 presented before. And again, there's a picture with tag condensation, which I'll skip in the view of time. And so there are other dynamical questions you can ask, which I'll skip, which amounts to asking whether stability is present for the endpoint that I presented, namely the combination of D2 with D0 flux. I'll skip that, and I'll just jump to the key lessons. So in this talk, hopefully, I've presented some interesting interplay between QFT dynamics in the presence of defects and symmetries. And we have seen that upon deformations both on the bulk and the defect, topological defects can actually retain much of its structure under those deformations, such as fusion and a certain subset of F symbols. And even if in the context where the symmetry preserved by the deformation is featureless in the bulk, because of its interesting interaction with the defects, which become non-topological, it can lead to non-trivial anomalies, which can be used to deduce non-trivial dynamical consequences for the behavior of a defect under those deformations. And we have given explicit examples of non-topological defects which transport the topological defect we know in the sigma-1 moduli space to any radius of R for any ZK duality. And we have also seen this kind of dynamical process of taking the square root of a projector, getting a non-topological version of Tamaramagami type defects. And we have seen how this picture is represented in open string tag condensation context, and the corresponding anomaly that's preserved by this defect RG flow is matched by fuzzy torus from the D2 brane picture. And the spirit of this analysis, to take away a kind of spirit of analysis that I consider here can be thought of as some generalized version of the spirit analysis. All right, so there's a number of future directions. So first of all, it's interesting to understand more systematically constraints coming from these anomalies on defect dynamics. For example, some notion of symmetry reached G theorem. I have some thoughts on that. I welcome you to talk to me afterwards. And it's also interesting to understand dynamical implication of this symmetry constraints, in particular in the presence of a defect, for example, in the context of scattering problem with non-topological defects in massive QFTs, and some recent work in this direction. And it's also interesting to understand whether the discussion over here can teach us something about open-closed tag condensation from the worldsheet perspective. And also, I think it's interesting to revisit this question of symmetry surfing, which is an important idea, trying to understand the problem of Matthew moonshine, using this non-topological defects as a way to transport symmetries. And finally, it will be very interesting to understand universal structures for defects, and in particular, their interplay with defect fusion. Some of these quantities involve the transformation of information energy and dissipation. It'll be interesting to understand their interplay with RG and also under fusion. Okay, with that, let me thank you for your attention.
Question? So many questions.
Thanks for the very wonderful talk. So I have a question. Will the defect anomalies affect the defect fusion rules?
Sorry, where are you?
Here.
Sorry,
here.
yeah.
So will the defect anomalies affect the defect fusion rules?
The defect anomaly will the defect affect fusion rules. The short answer is I don't know in general. In this case, it does not, because we're considering a very specific kind of symmetry and a specific kind of anomaly. The fusion rule is very constrained just by the fact that we're preserving Z2 symmetry, and the starting fusion rule just fuses into the projector. But more generally, I don't know the answer. Yeah, that's a good question.
Can I?
Sure.
Thank you for the talk. In your setup, is UL and UR a specific representation of the underlying fusion category of defects, or what was it?
So you can think about the UL and UR carries information more than the Z2 symmetry defect, and the more information is hidden in the choice of the junction between the topological defect eta and the defect N, which becomes non-topological away from the special point.
Right, so the projective phases that come out of this, is that uniquely fixed in your setup?
There is always gauge redundancy, but in the gauge I'm using, they are fixed, yes.
Okay, cool,
Yeah.
thank you.
So the point is that you can move the phase around, but you cannot eliminate them altogether. So the point I'm making is that I'm using the gauge where the Z2 property, namely UL squared and UR squared is equal to 1.
Okay, amazing.
So you can move the sign elsewhere, but you cannot remove it totally. Yeah, that's a good question.
Jake.
So the defects you considered are very closely related to the topological interface between the type 2A and type 2B worldsheet theories.
Yeah.
So I wonder if you have thoughts on the relationship of what you discussed with the domain wall and target space.
That's right. So indeed, when I was preparing for the talk, I had thoughts on that. That's precisely what I meant by the third bullet point. But after discussing with many of you, I don't think I have anything clever to say, apart from the construction that people already know from half gauging. Perhaps one answer I can offer is that I can, of course, I can give you examples where the topological way of defining those interfaces on the long string worldsheet can also be generalized to the case of non-topological versions, like with non-zero tension. But of course, the usual questions, which is the problem that we don't really have the perturbed string worldsheet, like a fundamental string worldsheet description for this interface, still exist.
Do you see any implication for its stability for the domain wall and target space?
Right, that's a very good question. So I did not have time to discuss that part, but actually in the example I discussed, there is a symmetry protection against instability. So that may be relevant, yeah.
Thank you.
Yeah.
Okay, we can postpone the question later. So let's thank the speaker again.
Good evening, everyone. It's my distinct pleasure and privilege to welcome you at the closing ceremony for Strings 2026. As we gather here in this final evening, it feels like we have just blinked and the whole week has passed by. Yet, when we look back at the sheer volume of the science we have discussed, it feels like we lived a lifetime in just 5 days. Let us take a moment to appreciate the sheer magnitude of what we have accomplished together. Tonight, we are here to celebrate the end of a remarkable event, but more importantly, to celebrate us, the extraordinary global community bound together by our shared passion for fundamental nature of reality. It has been challenging, brilliant, and joyful journey, and I am honored to be here with you to bring Strings 2026 to a closure. Thank you for all being here. Let's begin our final program. It's my distinct pleasure to introduce our first speaker, Professor Shintan Yao, Chairman of the Strings 2026 Fields Medal Laureate, Chairman of the Shanghai Institute for Mathematics and Interdisciplinary Sciences. Professor Yao, please come to the stage to deliver your remarks.
Well, dear friends, colleagues, ladies and gentlemen, good evening. We have made it to the end of the 5 truly remarkable days. As chair of the String 2026 conference, I'm incredibly happy to welcome you all to this closing ceremony. Looking back at the past 5 days, it has been an absolute privilege to watch the program unfold here in Shanghai. We start Monday morning with Andy Strominger taking us through soft algebras and holomorphic symmetries, and from there, the momentum never stopped. We have listened to so many brilliant talks from so many string masters. The sheer breadth of ideas shared here has been deeply inspiring. I would like to thank every single speaker to your amazing talks and amazing accomplishments, and for so generously sharing your latest insight with us. Over the years, people have occasionally asked about the direction of string theory or where it is leading us. When I look at this discussion from this week, the answer is incredibly clear. String theory is not just a model, it's a profound intellectual journey that continues to power and transform the landscape of both modern mathematics and modern physics. It forces us to invent new mathematics, to understand the physics, and use physics to unveil beautiful hidden structures in math also. We all honor the great hope that someday string will help us to unlock the deepest, most fundamental secrets of nature, but a challenge that takes time, patience, and fresh perspective, not to mention a lot of funding that we are looking for. To the young researchers and students in the room today, this is where you come in. Do not be intimidated by the scale of these problems. Accept the challenge. Take the ideas you have heard here this week. Push them further, question the assumptions, and bring your own energy into the field. The future of this journey belongs to you. None of this would have been possible without an incredible team working behind the scenes. I wish to extend my greatest gratitude to the scientific and organizational committee and all the staff here that help us from Siemens and from the Fudan Center. Your tireless hard work, attention to details, and dedication are what make this such an impressive, smooth, and genuinely beautiful conference. Let's give them a big round of applause. So finally, thank you for all of you who traveled to Shanghai and for bringing your passion to String 2026. I wish you all a safe, comfortable journey home, and I look forward to seeing you where your research takes you next. Thank you very much.
Thank you, Professor Yao, for your thoughts. It is a long tradition of Strings Conference to announce the host of the next conference at the closing ceremony. To make an announcement, I welcome Hiroshi Oguri, Chairman of the Strings 2026 Scientific Committee, Professor at California Institute of Technology and University of Tokyo, Eisenhower Prize for Mathematics and Physics laureate.
Hey, thank you. Can you hear me? So let me first set this thing up. Let's see how it works. Okay, so let me set it up. Okay, so this is meant to be concluding remark. But on behalf of the String Planning Committee, first I'd like to invite Timo, Alexander, and Craig to the podium.
Yeah, hello everybody. On behalf of our colleagues at the Mathematical Physics and String Theory groups at Hamburg University and DESY, whose name you can see here, we are super excited to announce that Strings 2027 is going to happen in Hamburg. So as you see, the conference will be a little bit later than usual in September, the first or second week of September, 6 to 10. This is the week right after Eurostrings in Birmingham. So those of us who are planning to come from farther apart and maybe combine both events can do so in a more economical and also sustainable way. And in fact, of course, the amazing and spectacular event here in Shanghai in 2026 sets very high bars on the organization of the conference, but we are extremely motivated and excited to try our best to welcome you all and be as good hosts as possible in Hamburg. So in fact, maybe Hamburg is the natural next host because Shanghai, the host of 2026, and Hamburg have been twin cities for 40 years. This is a partnership that started in 1986, so shortly after the first string revolution. Indeed, both cities share some similarities. They are both located on big streams, rivers. They are cities of big ports. Here you see a cartoon of the Hamburg port with a big ship, and you also see the Hamburg Philharmonia Hall, which is one of the hallmarks and where strings play an important role, maybe in a bit more literal sense. You also see in the front the old university building in the city where we are planning to host the meeting. And finally, let me remark that harbors and ports, cities with big ports, are natural places for an influx of goods and also for an outflux. So in this sense, we are hoping for a large influx of many of you to Hamburg next year. And of course, so that you all help us create an outflux of new insights and ideas in string theory from Strings 2027. See you next year.
Welcome to Hamburg.
Thank you very much. So this gives us something to look forward to next year. So I was asked by the organizer to give you half minutes of entertainment. So that's what I'm going to do at the end of this wonderful conference. First, I was the chair of the scientific program committee in charge of the selection of plenary and review speakers. So I thought I should review some of what we have done. So we have this string planning committee that chaired by David Gross, and our friend in China reached out to us and then suggested to have Strings conference. And then it was officially announced on July by David Gross. And then in September, we are asked to be on the scientific program committee. So this is a member of the committee. And the committee charge was to determine the format of scientific portion of the conference and select plenary and review speakers. And then the local organizer was very gracious to include the sentence that the committee should have autonomy. And so we had freedom to choose speakers based solely on scientific merit. And we are very grateful that local organizer actually honored this commitment. And then I believe that you have seen the consequence of this wonderful list of speakers. And so I thought we should discuss a little bit about the demographic of plenary and review speakers. And of course, demographic is something dangerous to talk about. And, but the compliance officer of my university tell me that the PhD year is not protected characteristic, so we can talk about it. So here is the academic age of plenary and review speakers according to the, so these are black, the red are postdoc, purple junior faculty and senior faculty. You see that the majority of speakers are actually within the first 20 years, from PhD, starting from postdoc, going to junior faculty, and more senior faculty member. But then if you look at this, there is, of course, this distinguished group of people who have made foundational contribution to string theory and continue to be leading the field. But if you look at this, there is actually, after this, there is more than 10 years of the gap until you get to Juan Maldacena and Marcos Marinho. And then I was wondering, by looking at it, who are people in this lost generation? And I realized that I'm actually right in the middle of this. And there is another observation I can make, which is that discoveries and breakthrough characterize generations. So, and of course, there is a superstring revolution here, and then second superstring revolution, also known as string duality revolution, and then ADS-CFT correspondence. But these are not only discoveries and breakthroughs that shape the generation. There are many, many ideas, beautiful ideas, and powerful tools developed. For example, this year is the 50th anniversary of Yau's proof of Calabi conjecture, which we'll be celebrating in September in BIMSA. And these discoveries were indeed important ground for the superstring revolution. And so these discoveries are not made in isolation. For example, we see a lot of talk about related to review theory or matrix model, and these happened over here. And then there is a continue to be beautiful parade of ideas and powerful techniques continuing. So there are lots more to look forward to. We can also talk about the geographic distribution of plenary and review speakers. So here, red dots are Asia, purple are Europe and Canada, and blue is USA. And you see that there are a little bit more US speakers, but in the younger generation, there are many from Asia. But if you look at PhD institutions, it's actually majority of them are USA, which means that many of the speakers got PhD in the US, but then in Europe and Canada also. But since this, if you look at this, there are lots of people, young people, active people in Asia. So that would mean that in the next 10 years or so, there will be more speakers from Asia, one could expect. Just for comparison, here is a demographic of the committee member, which is evenly in Asia and USA and Europe, as you can see. So this is how sort of we selected the speakers. So with that, I thought I had done my job and would enjoy Strings Conference as a participant, but it didn't work out that way. That Slava Risov wrote to me about a couple of weeks ago, saying that some of the local organizers liked your review talk at Strings 2024, and he wanted me to do the same thing. So first I had to remember what I did 2 years ago. And at that time, actually, Andy Stroming and I led the discussion in the closing session. And we actually collected questions from the string theory community. But we thought that the big questions like unifying quantum theory and gravity may not be sort of not so easy to discuss. So we asked questions that can plausibly be answered within the next 10 years. And then we collected 100 questions, and these are still available at the Strings 2024 website. And then we use that to discuss some of the development of string theory at that time. So I thought, well, following up on that and honoring the request by Slava, what can I do? And then I remember that, well, now I'm sort of also the division chair of the physics, mathematics, and astronomy. So I remember that I realized that in university, actually, if you have a tenure track faculty member, we have a committee that monitors the progress towards the tenure. So I thought, well, maybe you can try something similar, which is to ask those who had submitted questions before, 100 questions, and other colleagues, and ask them to provide their candid assessment of our progress over the last 2 years. Namely, that are we on track to solve these questions within the next 8, namely 10 minus 2 years? And should we keep some of the questions or revise them or perhaps retire them? Namely, is string theory on track to earn tenure? So we got 59 responses. Some suggested they want to keep the original question, some revised and updated after 2 years. And these questions are available at this Strings Conference website. So I organized these questions into various different categories. The largest group of questions were about worldsheet, which is very interesting. So worldsheet description continued to be actually important ingredient in string theory. So the Ova Faroni actually sent me the first questions and a response, and he actually wanted to keep the original question, which was, what is the classical string theory dual to large n limit of 3 plus 1 dimensional QCD? And he said that I'm still hoping that it can be answered in 8 years. We are close to answering the analogous question for 2D QCD, but of course, that is a much easier case. And Igor said that perhaps in n equal 1 case is tractable and suggested a way to find string dual. And then there are also Viktor Gorbenko and Leonardo Rastelli provided similar questions. There are several people who have asked questions about worldsheet formulation of string theory in ADS, and so both from the point of view of ADS Virasoro-Shapiro model description and generalization, but also top-down, sort of, or bottom-up, should I say, description in terms of ADS3 background with Ramon flux. Matthias Gabadier says that they are beginning to get ADS3 background with Ramon flux under control. And Rajesh Gopakuma asked, can we use conformal bootstrap constraint to gain insight into string worldsheet in ADS? And in fact, there was a talk by Shai Chester related to this question. There are also outstanding questions about how to describe worldsheet for non-stationary background. This was asked by Nikita Nekrasov. And he pointed out some interesting paper by Chianti, Eberhardt, and Misera. So actually, I'm planning to study some of those papers. Space of theories is another interesting topic that has been lots of discussion on this subject at this conference. So one possible way to approach it is to look at the situation with large number of supersymmetry. So Mike Douglas suggested he wanted to keep the original question, which is, is there a simple description of the complete set of all string M-theory compactification with 8 supercharges? And Leonardo Rastelli wanted to use a bootstrap to classify space of consistent superconformal theory. And he pointed out that for maximally supersymmetric theory in D equal 4 or 6 dimension, embedding string theory and M theory suggests that we already possess complete list. And asked, why can't we put it on the rigorous footing by purely field theoretical argument? And I think there is actually a path toward doing something like that. For example, let's take n equal 4 superconformal field theory in 4 dimension. Of course, n equal 4 super Yang-Mills is an example, but is this the only example? So one way to think about that is that, well, it has a unique stress tensor multiplet. So the conformal manifold is one-dimensional and it is locally hyperbolic. So the question is that, is there infinite distance limit in this conformal manifold? What happens if you go to infinite distance in that direction? If it becomes free theory, then you can see that, you can only have n equal 4 super Young mills. So this is like one way to approach this question. And this is actually closely related to the distance conjecture. So distance conjecture is now celebrating 20th anniversary this year. And this is what Kumran and I formulated, starting with the conjecture that every parameter in quantum gravity is the expectation value of some dynamical field, and that moduli space has infinite diameter, and if you go to infinite distance, there is actually an infinite of light particles starting with a mass of order exponentially suppressed, e to the minus alpha phi. So Timo Weigand gave a beautiful summary of current progress in understanding this conjecture. And so, in fact, the CFT version, ADS CFT version of this conjecture has had lots of progress in the past couple of years, and we have gained quite a bit of insight in the CFT version of distance conjecture. So there are lots of things that we can still do in this direction. I think one of the surprise at this conference was talk by Jake McNamara, who actually presented a claim that unitary quantum field theories are determined by the closed manifold partition functions, and every reflection positive partition function arises from a unitary quantum field theory. So in some sense, this function, which is the partition function, can be used in this kind of classification program too. Although this work was originally motivated by some of the holographic questions that raised by Jianbin Yang, raised in the review talk by Jianbin Yang. But this can be stated as a purely quantum field theory statement, and can be relevant also to this question of understanding space of quantum field theory. So symmetry is also another element that is very interesting to look at. So in this context, one interesting direction to think about is that quantum gravity is supposed to not to have global symmetry, but then the question is that can we quantify how symmetry can be broken, for example? So those are that's a question that asked by a couple of people. Miguel Montero amended his question that he submitted 2 years ago, and now he says that can we precisely quantify or prove bound on the amount of breaking of global symmetry in quantum gravity? And then Julio Paramartinez asked a similar question, but in this formulation, that is there a lower bound on the on the cross section implied by no global symmetry in quantum gravity? So holography continued to be inspiration for many progress in string theory. And Juan asked 2 years ago that could we understand better any holographic example relating matrix integral to Euclidean gravity solutions that are described by Einstein gravity. So KKLT was in fact proposed many years ago as an example of this. And then, in fact, after Juan asked this question 2 years ago, immediately after that, there have been a couple of very interesting progress in this direction, identifying the holographic pair by deforming the original version of KKLT matrix model. So there can be interesting progress in this direction too. And Andy Strominger asked, is LW1 plus infinity a symmetry of string compactification for the flat space? And he himself actually provided some evidence that there is a progress in this direction by considering the ADS CFT version of this question. Uniqueness of string theory is another interesting question. So, this is an area where there have been some very interesting progress, and Cliff Chun reviewed this progress. So Grant Lehman revised his original question. 2 years ago, he asked whether you can actually, the string amplitude can be unique under certain condition. But since then, more recently, he did this work with Cliff and the collaborator. So he amended the question by saying now that we have found a set of S-matrix bootstrap conditions that uniquely output the mass and spin spectra, as well as the amplitude, can we physically motivate these requirements or weaken them? In fact, this work is interesting in the sense that it sharply defines under what assumption string theory can arise. So you can ask whether these assumptions are reasonable or whether we can weaken the assumption, etc. So this can be a starting point for the question of uniqueness. So finally, there is also a question of definition. So Daniel Harrow sent me this question that quite a lot, perhaps most of the progress of quantum gravity in the last 20 years has happened using methods that, although partly motivated by string theory, do not rely on the detailed UV structure of the theory. On the other hand, progress toward finding a general non-perturbative formulation of string theory has largely stalled. Now, I disagree with this claim. However, since he's not here, I do not feel I should make rebuttal in his absence here. So instead, I would like to suggest a couple of areas where progress has been made. And one is the string field theory. So Monkey Kim asked, well, can be formulated non-perturbatively? And can we learn something about non-perturbative physics from string field theory? In fact, string field theory was reviewed by Ashok and discussed by a couple of speakers. And then in the discussion session on definition of amplitude, there were a lot of discussion about string field theory. So it's clear that string field theory is very useful in organizing and calculating ambiguously perturbative amplitude. There has been some use of string field theory in getting glimpse of non-perturbative physics, such as open string tachyon condensation by Ashok Sen. But I think that now that string field theory has been established as actually a complete description of perturbative string amplitude, perhaps we can push this further and try to gain some non-perturbative information from here. Another way to gain non-perturbative definition can be resurgence, and there have been several questions in this direction, and this was discussed by Marcos Marino today. But this description might not give a complete definition of string theory, as pointed out by Slava Rychkov, and he asked, can we actually axiomatize a notion of string theory? Well enough so that a statement like there is a dual string theory description of gauge theory, or there is a dual string theory description of critical 3D Ising model become sharp questions allowing, at least in principle, yes or no answers. So with his questions, I just pointed out where the questions have been organized into these 6 areas, and each has had lots of interesting ideas and many sources of further progress, and there are lots of things to look forward to. But in fact, I still have one more wish to solve, which is a question about machine moonshine, because this was actually the calculation I did in my PhD thesis many, many years ago. And only after 21 years, we figured out that these expansion coefficients are related to Massieu group. But the origin of this is still not well understood. At least Greg Moore thinks it's an interesting question. And then Ifan just suggested maybe there is a way to address these questions. So I think that this is actually still very interesting questions. Maybe perhaps after 20 years, maybe 2030, by 2031, we may be able to finally understand where these symmetry come from. So maybe we can say that string theory has not earned tenure yet, in the sense that it has not been experimentally confirmed, but it's very promising. And if I were the department chair, deciding this reappointment of string theory, I'll be very pleased to reappoint string theory as a candidate for fundamental laws of nature, that we are very impressed by what string theory has accomplished, confident in its trajectory, and excited about its potential to identify the fundamental laws of nature. So scientists are like travelers without maps. String conference provides us an oasis to pause, compare paths, and see how far we have come. As Shin Chiji of Southern Song Dynasty wrote in his poem, Chen Shi Ju Bu Ju, Beijing Dong Liu Chu. Great mountains, green mountains cannot stop the river. In the end, it flows eastward, which means toward the sea. May the idea and techniques discussed at Strings 2026 continue to flow, and may we have great fun discovering where they lead. So I could have stopped my concluding remark with these uplifting comments, but I feel that I need to address the elephant in the room. So I'm going to say something, and if you feel compelled to boo me, you can do that, but please keep it brief so that I can continue my remarks. So I'd like to discuss impact of AI on string theory. No? Okay. So in the case of AI had lots of impact already in the research in string theory, but I don't think anyone can confidently predict what capabilities that AI will acquire over the next few years. So we cannot even ask similar questions in the 10-year time scale. So instead, I asked the same group of people, which aspect of AI and the future practice of string theory should our community be considering now? And what would you say to graduate students beginning string theory today about the possible role of AI in their scientific life? So we got a lot of interesting responses. Some group of people say that, in fact, it gives a very large verified knowledge basis. It's curated and reliable, and it can help to identify unexpected connections. Julio Para-Martinez said that, in fact, the bottleneck of many programs in our field is not intelligence, after all, but attention. So he expressed a hope that AI will cure this bottleneck by solving all the problems solvable with the current tools and leaving the interesting hard one for us to explore. It also helps us, in that vein, it helps us ask new kind of questions, namely that change what kind of program we would even find tractable. And Julio also says that if agentic LLM loop can solve your problem, perhaps you need to find a better program. So I think, as Andy says, that I'm cautiously optimistic that we learn a lot from using this tool. Of course, we have to be very careful in using it. Verification should always come before belief, as Shurdeep correctly said. And Ricardo Schiappa says that perhaps we should consider writing less paper, but better paper, and much harder paper. So that's an interesting suggestion. Creativity is something people are unsure whether AI can acquire. So Nikita says that perhaps for graduate students, foundation creativity and authenticity is even more precious. And we should develop more of the ability to come up with ideas. But we don't know. AI might acquire such capability in the next few years. And Greg asked, will a human HEP-TH physicist working with an AI agent find that agent and not the human has formulated a truly new and beautiful idea? In fact, some of what I consider to be most creative member of our community said that openly consider the possibility that AI would overtake us in this area. So for example, Ashok Sen said that if eventually it overtakes us and solve the problem of quantum gravity and all other forces, I'll be happy. And Yuji Tachikawa says that I don't think the reasoning capability has an upper bound given by the genetics of Homo sapiens. So therefore, I won't be surprised if AI might become vastly superior to human in the ability to do theoretical part of research, and she seems to be okay with it. So you see, lots of people have different view on how this is going to go from now. But among many of these ideas, the one that I like most was from Juan Maldacena, who said that I would tell graduate students to ignore what I and others in my generation say about AI. That I would encourage them to learn to use it in novel ways to solve physics problems. I think that's a very good suggestion to us, I think. So those are all very interesting suggestions, and of course the question would be what AI would think about such responses, and of course I asked that to ChatGPT, and here is the response. I asked, what do you think of these responses, and says, they are reassuring. I especially enjoy the recurring hope that AI will remain a tool. Future historians may find that adorable. I didn't make it up. I could have made it up. So this is what the ChatGPT said. Okay, so good luck, humans. The next few years will be very, very interesting. So as the String 2026 draws to close, I'm reminded of Tang Dynasty poem by Wang Bo, written as he was bidding farewell to a friend. 海内自己之，天涯若比邻。 With two friends across the world, even the end of the earth feel like close neighbors. Many of us came to Shanghai from faraway places to meet, discuss, and learn about the latest development across string theory. Thanks to the warmth and hospitality of our host, Strings 2026 has felt more like, not like being away from home, but like being part of one shared community. So even the end of us feels like close neighbor. So on behalf of all of us, I would like to say, 衷心感谢大家 und auf Wiedersehen in Hamburg. Thank you very much.
Thank you, Professor Oguri, for your efforts in collecting and summarizing opinions of string theory researchers worldwide. Some of the participants come to me to express their gratitude for organizing the conference, but I didn't run this conference alone. I want to use the closing 5 minutes to mention all the great people whose tireless efforts made this conference possible. Let me start with Chair of Strings 2026, Professor Shintan Yao. Chair of Local Organizing Committee, Professor Bon Lian. Local organizers, Hamid Adami, Kim Yon Lee, Andrei Losев, Slava Lysov, Wenjin Ma, Satoshi Navata, and Hao Zhou. Scientific Program Committee, Rajesh Gopakumar, Julio Para Martinez, Alexander Westphal, Andrei Losев, Michael Green, Sergei Gukov, Janet Hank, Zohar Komagotsky, Hong Liu, Tadashi Takayanagi, Irene Venezuela, Shein, and Hiroshi Oguri, the chair. Thank you. Our beautiful secretaries. Our great IT staff. Our student assistants. Other assistants. So I noticed that many of you already accepted invitation to speak at International Congress at Basic Science that we will have in August of this year in Beijing. So hence, I will use this opportunity to invite all of you to come to Beijing to attend International Congress of Basic Science this year. So thank you all. See you at Strings 2027 at Hamburg.